Okay, good evening. Can you hear me? Good evening, can you hear me? Thank you. Yeah. So yesterday, due to some technical problem, the class was cancelled. Fine. I think this is the problem where we have stopped yesterday. Am I right? Is this the problem where we have stopped? Yes. So in the previous problem, in the place of 1 volt, we had a current source. Am I right? We had a current source. So we took the same current. The same strategy we will apply here also. So let's take some current I here. Whatever current comes from the positive, the same current should enter the negative terminal. And this current will sink through the op-amp. Right? And voltage difference between the two terminals is 0 because the voltage at plus and the voltage at minus both are same. So when you take the difference, it is always 0, right? So let's apply KVL in this loop. Let's apply KVL in this loop. So minus to plus, minus 1 plus I into 3K minus 0 plus I into 2K is 0. So what is I? It is 1 by 5K. The current I is 1 by 5 kilo ohm, right? Now, how do we find V naught? V naught is the voltage at this point with respect to ground, right? So to find V naught, we can take a loop here. Here. So one more KVL. I into 5K plus 0 plus I into 1K plus V naught equal to 0. So what is V naught? Minus I into 6K. So let's substitute minus 1 by 5K into 6K. So what is 6 by 5? 6 by 5 is minus 1.2 volt, all right? So I repeat, we have two loops here. One chota loop, one a little bada loop, right? So minus 1 plus I into 3K minus 0 plus I into 2K is 0. And the other one is I into 5K plus 0 plus I into 1K plus V naught is 0. So this is the loop here, right? From ground, you come back to the ground node. So your V naught is going to be minus 1.2 volt. Okay, so what was the second problem? Yesterday we missed. Is this the second problem? Have you done it? Anybody has answers for this problem? Anybody has done this problem? You have any answers? Any answers for this problem? Any answers for this problem? Very good, right? The best part is you have tried. Now, the best way to learn is by trying. Wow. What is the outcome? That is immaterial, but you have to try. And there are so many people who have shared their answers, right? I'm pretty happy. But I'm not right now checking whether it's right, correct, or not. It's immaterial. So what is important for me is you have given a good shot, right? That is more important. Because once I solve the problem, you will know the answer. So my intention is not the answer. How many people have tried? That is more important, right? Great. So you can make, yeah. How do we solve this? How do we solve this? The 1 milliampere current this time is entering this node. Am I right? And now that current is split into two currents. What are they? I1 and I2. So I will apply KCL. What is KCL? The current entering the node is equal to the current leaving. So 1 milliampere is equal to I1 plus I2. So any problem with this? No, is it not? 1 milliampere is I1 plus I2. And what is the voltage difference between the two terminals? Is 0, right? Now, can you see a small loop here? I mean, you might not see such a small loop even in your networks class, right? So this is a small, very, very chota loop. From where does it start here? The dot, right? So you go all the way I1 into 2K minus 0 minus I2 into 3K. Can you see the small, very, very small loop there, right? So yeah, very, very small loop. So what's the smallest loop you can expect here? Just two resistors. And op-amp tries to keep the potential as 0, right? So here you have 2K. There's I1. This is 3K. So you can have the smallest loop and the smallest KVL you can ever think of, right? So it's I1 into 2K minus 0 minus I2 into 3K, or I1 into 2K equal to I2 into 3K. So the first equation says I1 plus I2 is 1 milli. The second equation says I1 into 2K is I2 into 3K, right? So from 1 and 2, what is I1? I1 is going to be, or if you remember current division formula, that is also fine, because current division can always be applied if two resistors experience the same potential difference and the current has to divide, right? So you can see that this node is same for both the resistors, and this node and this node both are same. So that means I1 into 2K is same as I2 into 3K, and the current is dividing. At what ratio will it divide? I1 is going to be 1 milliampere into 3K by 2K plus 3K. So it's 3 by 5. It's 0.6 milliampere. Then what is I2? I2 is 1 milliampere minus 0.6. It's going to be 0.4 milli. Just tell me, what is the drop across 2K? What is the drop across 2K? It's 0.6 milli into 2K. So 0.6 into 2 is 1.2. What is I2 into 3K? I2 into 3K is 0.4 into 3. 0.4 into 3 is 1.2. Yeah. So 2K into I1 and I2 into 3K, both are experiencing same potential. They may not be in parallel. We don't say that they are in parallel. Parallel means what? Parallel means both ends should be tied together, right? But only one end is tied here. The other end is the op amp tries to keep those two potentials same. So if two resistors experience same potential difference and the current is dividing, you can apply current division. Or if you don't remember current division, no problem. I have given you two equations. If you solve them, I1 and I2, you get 0.6 milli and 0.4 milli, right? And where does I2 go? This I2 is the same current through 5K, and I1 is the same current through 1K. I1 is the same current through 1K, right? And you have V0 here. V0, all right? Okay. In the previous problem, we applied KVL around this loop. In the previous problem, we applied KVL around the loop, and we're going to follow the same discipline now. So let's follow the same discipline. We just go around now, KVL. Minus I2 into 5K plus 0 plus I1 into 1K plus V0 is 0. Plus V0 is 0. But what is I2? I2 is 0.4. 0.4 into 5. Help me, 0.4 into 5. That's 2. And I1 is 0.6. So 2 minus 0.6. So V0 is 1.4. V0 is going to be 1.4 volts. V0 is going to be 1.4 volt, right? So this is similar to the previous problem. We applied the same KVL. So it's just a kind of a practice, right? The only difference is we have taken the entering current equal to leaving current, and then we've tried to find I1 and I2, right? Then we substituted by applying KVL in this loop. Now, if I'm applying nodal analysis, I can take VP here and VN here. What is VP minus VN? That is 0, right? So VP is some voltage, VP and VN both are same, and VP minus VN is going to be 0. So when will we take 0? When you're applying KVL, we deal with the drops. When you're applying KCL, you deal with the nodal analysis. So we can take VP here and VN here and apply entering current equal to leaving current. But this is not entering current equal to leaving current. It's a sum of voltages in a loop. I need voltages, right? The sum of voltages in a loop should be 0. So you can take VP here and VN here. What is VP minus VN? The potential difference between plus and minus is VP and VN are same, right? If this is X, that is X. So X minus X is 0 volt drop, right? So I'm taking VD there. What is VD? VD is 0 because VP is same as VN, right? Okay. And how about this problem? Have you done this? Now, you can solve the previous problem by applying KCL also, right? You can apply KCL. I've taken KVL just for a change because you quickly get the answer. You can apply KCL. This doesn't matter, right? It's not a debate whether you should apply KVL or KCL. Because if you apply KCL, there are more nodes now, right? So there's node 1 here, 2. So you can apply 2 equations. For me, once I know I1 and I2, because I know all the currents, and with a single loop, I can find the whole voltage, right? Or you can apply KVL like this through 5K and 3K and 2K and 1K and then V0, like that also, right? So you can take any loop. So loop means what? The starting point and the ending point should be same. So you just go around. How you want to travel is left to you. You can take 5K and then 3K and then 2K and then 1K and then V0. 5K, 3K, 2K, 1K, V0. Like that also you can travel, right? It's your wish. Or you can apply KCL, like how we have done the previous problems. You can apply with KCL and try to confirm the same answer, right? Some problems I've done with KCL. Many problems I've done with KCL. Now I'm doing many problems with KVL also, right? Okay. It's just for practice. So how do we solve this? Now the same problem, when I take up positive feedback, I'm going to prove why this circuit is giving you negative feedback, right? So the same circuit I'm going to tell you. But right now, believe me that this is having what feedback? Negative feedback. So there's no beta n, then beta p. So we will calculate beta n and beta p later, right? So right now, all these problems which I'm giving you, apply what ground? Virtual ground, right? So you apply virtual ground. Now, how do you get VP here? VP, you can apply voltage division, or if you have forgotten voltage division, if there is some current I, the same I flowing, because op amp takes 0 current, right? So KCL, V0 minus VP by 10K equal to VP by minus 0 by 10K. Ground is 0. So you're going to do V0 equal to, or VP equal to V0 by 2. So this you can do by voltage division, right? VP is V naught into 10K by 10K plus 10K. So VP is V naught by 2. But this is same as Vn. This is same as Vn because of virtual short, right? So this is Vn. Now tell me, you have a 3 volts. This node is V naught and this node is Vn, right? So 3 volts is nothing but the potential difference between the two, right? So you have 3 equal to Vn minus V naught, which is V naught by 2 minus V naught is 3. So what is V naught? Minus V naught by 2, so it's minus 6 volt. Now, all of you, why is this op amp is settling down at minus 6? Why it can't be any other voltage? So it goes bang, 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 and then stays there at minus 6, so that your non-inverting and inverting voltages are same. So let's cross check. If it is minus 6 at V naught, what is VP? It's going to be minus 3. It's going to be minus 3. Then you try to backtrack from the 3 volt. If Vn is any other value than minus 6, if V naught is any other value than minus 6, can you have 3 volts in between? Because your Vn is going to be half of that, right? So what is half? Vp is going to be minus 3. So minus 3 minus of minus 6 is going to be 3, right? So it's just trying to cross check. I'm just trying to cross check. This is 3, which is the potential difference. I'm saying this is minus 6, and then tries to backtrack and brings minus 3 here, right? So what is the difference now? Minus 3 minus of minus 6 is going to be 3 volts, which is this voltage, right? It's the potential difference. So op amp output cannot be any other value than minus 6. It has to settle down at minus 6 just to keep the two potentials same, right? Okay. Any other questions I've given yesterday? I mean, because of technical problem, we had to wind up. Very good. Minus 6 is the answer. Yeah, in all the problems, we are taking op amp as ideal, right? Unless and until I mention, if an op amp problem is given, it's ideal. It's ideal means the gain is infinite. If the gain is infinite, then VP and Vn both are same. They are almost at the same potential, and the error between the two terminals is so small that we can always neglect it, right? So the VD is very small. It'll be microvolt. So 0 volt or microvolt, it doesn't matter. The final answer is outcome is going to be the almost the same, right? Now, in all the problems that we have done, I have never given the power supply, right? But if the examiner gives power supply, please look at the transfer characteristics, right? Without the transfer characteristics, you cannot solve such problems. The moment he gives a problem, just draw the transfer characteristics and later on do the same procedure. Doesn't matter. Whatever the procedure we have been doing, same procedure you do. But the discipline is first draw those 3 lines, right? The piecewise lines, transfer characteristics, right? That should be the discipline whenever power supply is given. If supply is not given, then this is at plus infinity and this guy is at minus infinity. The power supply limits are at plus infinity and minus infinity. That's the assumption, right? It never be infinity. The op amp does not work at infinite voltage. But when you're treating it as ideal, then you don't have to look at the power supply. So the examiner himself is saying that it's not going to saturate because this is at plus infinity and this is at minus infinity. It can take up any voltage, right? But now I'm giving you a simple non-inverting amplifier, but I give the power supply. So just do the same procedure, but draw the characteristics and then start, right? Find V naught. Find V naught or V01 and V02. Find V01 and V02. So this we can take it as a figure A and figure B, right? This is V02. Find V01 and V02. Find V01 and V02. Also find V plus and V minus or VP and VN. Also find VP and VN in both the cases, right? Okay, so let's get going. Let's solve for figure A, right? Figure A first. So in figure A, you can see that the plus VSAT and minus VSAT are plus 12 and minus 12, right? Plus 12 and minus 12. So how do you draw the transfer characteristics? How do you draw the transfer characteristics? And this transfer characteristic, what is this trying to infer? It's got three segments, right? Three segments. So it tells you that the op-amp can be solved in three ways, right? What is the first way of solving? The first way of solving is, if your VD is 0, then your V0 lies between minus 12 and plus 12. If your VD is 0, then your V0 lies between minus 12 and plus 12. If it's fine, if you get any voltage between, just your answer is done. But if it fails, then you have to go for segment 2. What does segment 2 tells? If V0 equal to plus 12, then your VD is greater than 0. It means your VP, your V1 is greater than V2, or VP is greater than Vn. If V0, if this also fails, then your answer is going to be, your V0 is going to be blindly minus 12, right? So you have to do only 2 times, because if you do 2 times and it fails, then automatically your answer is going to be the third case, right? So if you make an intelligent guess, then you can do it only once, right? Okay, fine. If it fails, first case, you can go for second case. If V0 is minus 12, then your VD is less than 0. That means your VP is less than Vn, right? So this is what the transfer characteristics tell you, right? So let's take case 1 now. Case 1. Let VD equal to 0 or VP equal to Vn. If VD equal to 0, VP equal to Vn, this is a non-inverting amplifier. After applying virtual ground, we know the answer. What is the answer? 1 plus R2 by R1. Am I right? If you have forgotten the formula, then if this is 1, this is also 1. Entering current equal to leaving current. Tell me. 0 minus 1 by 1K is 1 minus V0 by 9K. Your V0 is going to be 1 plus 9K by 1K times of 1. It is 10 volt. So your V01 is 10 volt. Now tell me, is it between minus 12 and plus 12? Yes, true, right? This is between minus 12 and plus 12. So if VD equal to 0, virtual short, then your V0 is between minus 12 and plus 12. True. So therefore, this is the answer, right? So V0 is 1 plus R2 by R1. So that's the answer we have got from the transfer characteristic. So whenever you apply virtual ground, your V0 should be 1 plus R2 by R1, right? This is case 1, right? Now, what about figure B? Figure B. What about figure B? Figure B, you've seen that the op-amp has supply only between plus 5 and minus 5. Op-amp has supply between plus 5 and minus 5. So what is the transfer characteristics for this? So it tells that if VD is 0, then your V0 should be between -5 and +5. What happens if it fails? What happens if the answer is not 5, it's 15 or 10 or 50, any other value? Then you can go to the second segment and say that if your V0 is at +5, then your VD should be greater than 0, which means VP is greater than VN. Or if this also fails, if V0 is at -5, then your VD is less than 0, which means VP is less than VN, right? So figure B, let me take the same problem, figure B. 1 volt, 1K and 9K, V0 2. So let's take case 1 now. The first case says that if this is at 1 volt, then your V0 is going to be 1 plus 9K by 1K into 5, into 1 is going to be 10. So now, if VD equal to 0, then your V0 should be between -5 and +5 is false now. It's false because the supply is very less. Suppose instead of 5, I've given only 1 volt, right? +1, -1. Do you think the output will swing to 10 volts for only a 1 volt supply? Here's only 5 volt supply, but the output wants to reach 10 in order to set up virtual ground. In order to bring back the same 1 volt, he has to run to 10 volts, but there is no supply. I didn't give supply. So though there is negative feedback, it is the inability of the op-amp that the output swing limits are decided by the supply limits. He's not able to reach to 10 volt. Why? Because the supply is only 5. With 5 volt, how you can get 10 volt output, right? It's not possible. So is it true that your output is between +5 and -5? No. 10 volt does not come between 5 and -5. My son can tell, right? It's integers between -5 and +5, you don't get 10, right? 10 is a number greater than 5, right? But the supply is only 5. Now we have to go for case 2. Now, just to avoid going for case 3, I mean, just tell me the next shot, what is the right answer? Because the maximum voltage is 10, so that means the output would have reached in what direction? The positive direction or the negative direction, and saturated. So it would have reached to 5 and probably saturated. So let's see. The case 2 says that if your V0 is at 5, then your VD should be less than 0, or VD should be greater than 0, or VP is greater than VN, right? So let's try the case 2 now. So I'm taking V0 as +5. This is 1K, this is 9K, right? Your VP is 1 volt. Your VP and VN are not same, right? VP is 1 volt, your VP and VN are not same. So let me apply entering current equal to leaving current. 5 minus VN by 9K equal to VN by 1K. So Vn by voltage division is going to be 5 into 1k by 9k plus 1k. This is going to be 0.5 volts. Your Vn is 0.5 and your Vp is 1. So if V0 is at plus 5, then is Vp greater than Vn? True. 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 Therefore, V02 equal to 5 volt is true. So what should be your answer now? In the first case, it is 10 volt, but in the second case, it is only 5 because the maximum supply voltage, so the op amp has saturated at what voltage? 5 volt. Now, why did it hit the positive rail? Because there is the maximum voltage that you can get, it is going to produce at the output, right? It can't be more than that. You can never claim that the op amp is going to give 10. How can it give 10 when the supply is only 5? What if I give 1 and minus 1 volt? It would have probably hit 1 volt, right? If I give 0.5 minus 0.5, it would have probably hit 0.5, right? So that means this is not a good design. So gate examiners will intentionally give smaller supplies and expect you to get larger outputs, right? So then you have to tell them that, I know this trick. You cannot get a large output from a small supply. So that means the op amp is going to hit the transfer characteristics and it is going to stop either at the positive rail or the negative rail voltage. So we don't have to check the other one, because if I produce V0 as minus 5, this is going to be minus 5 into 1k by 9k plus 1k. So it's going to be minus 0.5. So 1 minus of minus 0.5 is going to, VD is going to be again positive. So when the output is negative, your VD has to be negative. So the case 3 is going to fail if you want to take case 3. Case 1 is going to fail. Case 2 is going to fail. So this is going to fail. This is going to fail. And only this is going to get correct, right? So you can try all the 3 cases. And finally, your output is at plus 5 volt. And Vp is greater than Vn. What is the value of Vp? Vp is 1 volt. And your Vn is 0.5 volt. 0.5 volt, right? So the op amp has saturated at what voltage? Plus 5 volt. So there's no supply. The circuit shown is a capacitance multiplier. Calculate C equivalent. calculate C equivalent. Okay. So how do we calculate this? Whenever you want to calculate an equivalent capacitance, an equivalent resistance, or an equivalent inductance, it's always Ohm's law. What is Ohm's law? The equivalent impedance is always V by I, R equal to V by I, or V by I equal to SL, or V by I equal to 1 by SC. So the V by I is common for the impedance, right? V by I is R, V by I is SL, V by I is 1 by SC, right? So they are all ohms. Fine. So how do we find the equivalent impedance first? Let me connect a known voltage source here, right? A test voltage VT. Draw a current IT. Then the same current is going to flow. For the time being, let me treat this as an impedance Z, right? I'll treat this as an impedance Z. Now, according to virtual chart, if this is VT, this is also going to be VT, is also going to be VT. All right. Now, what is V0? This is V0. This is an inverting amplifier. Your V0 is going to be minus R2 by R1 times of VT. Your V0 is going to be minus R2 by R1 times of VT. Then what is IT here? What is IT if this is VT? IT is going to be VT minus V0 by Z, or VT minus V0 is nothing but R2 by R1 times of VT by Z. So VT by IT is going to be VT by IT is going to be Z by 1 plus R2 by R1. Z by 1 plus R2 by R1. Now, because it is a capacitance, I can replace this. This is nothing but V by I is nothing but your Z equivalent. Z equivalent is Z by 1 plus R2 by R1. Now, Z equivalent can be written as 1 by SC equivalent. Z is nothing but 1 by SC into 1 plus R2 by R1. So from here, what is the equivalent capacitance? The equivalent capacitance is going to be the capacitor that is being given multiplied by 1 plus R2 by R1. Right? This is the equivalent capacitance. It is C multiplied by 1 plus R2 by R1. So by adjusting the values of R1 and R2, we can have a larger capacitor, right? So because on a single IC, you can get 2 op amps or 4 op amps, right? So it occupies less space. And then by connecting 2 resistors and 1 capacitor, you can simulate a larger value of capacitor, right? So this circuit is called a capacitance multiplier. The capacitor is multiplied by the gain 1 plus R2 by R1. by adjusting the R2 and R1, you can have from a smaller capacitor, you can have a much larger capacitor. Z is nothing but 1 by SC. If it is an inductor, suppose instead of C equivalent, if it is L equivalent, what will you write? Z is nothing but SL, you have to write SL, or 1 by SC for capacitance. For capacitance, it's 1 by SC. Remember, for inductor, it's going to be SL. So therefore, your C equivalent is going to be C multiplied by 1 plus R2 by R1. So this is a capacitance multiplier indeed, is it not? Yeah, this is nothing but we have indirectly applied what theorem? Miller's, right? So Miller says that if the left plate is at this point and the right plate is at this point, what is the gain from this node to this node? The gain from this node to this node is going to be V0 by Vt. What is V0 by Vt? V0 by Vt is minus R2 by R1 is a gain. So what is the equivalent capacitance? C multiplied by 1 minus V2 by V1. C multiplied by 1 minus V2 by V1. What is V2 by V1? Which is V0 by Vt minus R2 by R1. So it's nothing but C multiplied by 1 plus R2 by R1. So this is also called what theorem? Miller's, is it not? So whenever a capacitor is connected, it should be ungrounded from this node to this node. So you have to calculate the gain from the left plate to the right plate. The right plate is at V0 and the left plate is at Vt. So the capacitance is, or what is the other way of doing it? Or C equivalent is going to be C multiplied by 1 minus V0 by Vt. Right? So you can just multiply. I mean, what is V0 by Vt? It is minus R2 by R1, so it's going to be plus R2 by R1. So this is from what theorem? Miller's. Okay. Now, with the help of capacitors and resistors, can I simulate an inductor? Is it possible to simulate an inductor using capacitors and inductors, right? Is it possible to simulate an inductor using capacitors and resistors? Such a circuit is called a gyrator. Such a circuit is called what? A gyrator. But what is the units of tau? Tau is nothing but RC, and which is seconds, right? And tau is L by R. So that means L is nothing but CR square. L is nothing but CR square. So if you want Henry, right? So if you want Henry, it has to be farad into ohms, right? Henry is nothing but C is in farad, farad into R square. Farad into ohms is Henry. So if you want Henry, if you want inductance, if you want to simulate the inductance, right? If you want to have the exact frequency response of an inductor, but you don't have an inductor on hand, right? If you don't have an inductor, then with the help of capacitors and resistors, you can simulate the property of an inductor, right? So that circuit is going to behave exactly as if you replace it with an inductor. So such a circuit is called what? A gyrator. So how are we going to do this? Gyrator. I want you to calculate the Z equivalent or the L equivalent here. And what is the name of this circuit? Calculate. Such a circuit is called a gyrator. This is called a gyrator. Because a student who has attended ISRO interview, right? So they asked him, is it possible that you get an inductor using capacitors and resistors? So what you have to tell them, yes, it's possible. Such a circuit is called a gyrator, right? But if you want to know how that circuit looks like, there are 100 ways of designing it. So this is one popular way of simulating L equal to CR square. There's so many ways of getting the same L equal to CR square. So apply the same procedure, connect a test voltage VT and find current IT. VT by IT is going to be a Z. And how do you write Z for inductor? Remember, how do you write Z for inductor? SL. What is Z for capacitor? 1 by SC, 1 by SC, right? So we can apply a test voltage here, right? A test voltage VT or VN, find current IN. By Ohm's law, what is the resistance? VN by IN. So if this is VN, this node is also VN, right? VN or VT, your wish. Let's see what are the nodes that we don't know, right? This I don't know what it is. Because I don't know and it's at the output, I'll call it V0, right? Any problem? No. But there's one extra node, this also we don't know. If you know the formula 1 plus R2 by R1, that's okay. But if you don't know, you can call it, what should I call? I'll call it Vx, right? So two unknown nodes are there, Vx and V0. But we want the ratio between Vn and In, right? Vn and In. Now, students are repeatedly asking, should I memorize all these circuits, right? See, you're going for a GATE exam. The examiner will give you have to write KVL and KCL. That's it, right? And if you see IES papers, mostly he is only giving the circuit and he's asking you to calculate the input resistance or the gain or the frequency response, bandwidth, all these calculations, right? It is not that you choose your own circuit and then do it. This is only for practice sake. We are doing it more. But yes, in an interview, he might give you a pen and paper and ask you to draw an adder or a subtractor. But simple adder, subtractor, at least you should be able to know, right? Okay. Yeah. I mean, if you want to become a lecturer, then you have to practice. There's no other go, right? But for a student point of view in the exam, he will give you the circuit, then you have to just apply KVL and KCL. Okay, so let's calculate. Let's apply KCL at Vx. Entering current equal to leaving currents. So there are 3 leaving currents and 1 entering current. But the good news is both these currents are going to op-amp. The good news is both the currents are going to op-amp. So op-amp draws no current, right? So let me apply KCL at Vx. What is KCL at Vx? Vx minus Vin by R equal to 0 plus Vin by R plus 0. So what is Vx? It is 2Vin. Or if you remember non-inverting amplifier formula, 1 plus R2 by R1. R2 is R and R1 is also R. So R2 by R1 is 2Vx. There's one more KCL here. Entering current equal to leaving current. Right? Oh, this is Vin. So this node is Vin. And this node is Vin. So KCL at the inverting terminal of the second op-amp. KCL at inverting terminal of second op-amp. KCL. Now tell me, entering is leaving, right? Capacitors you can replace by 1 by SC. So it is Vx minus Vn by R equal to Vn minus V0 by 1 by SC. That means into SC. But Vx is already 2Vn. 2Vn minus Vn, that is Vn by R equal to Vn minus V0. Vn minus V0. Can I bring the SC down here? SCR. So your V0 is going to be Vn minus Vn by SCR. All right. Okay, so that's it. Now tell me the answer. What is IN? Op-amp draws no current. This is IN. That's what we want. What is IN? Vn minus V0. IN equal to Vn minus V0 by R. It is Vn minus V0 is Vn minus Vn by SCR by R. So Vn gets cancelled. Vn cancels. Minus of minus is plus. Vn by In equal to S into CR square, which is S into L equivalent. SL. If it's a capacitor, 1 by SC, right? So SS cancels. So whenever I say S into something, it has to be an inductor, right? Therefore, L equivalent equal to CR square. L equivalent equal to CR square, right? So this circuit is a gyrator. It's a gyrator. So please don't forget right? So don't forget that whenever I say, whenever I say 1 by 2s, what is it? Whenever I say 1 by 2s, what do you mean by this? It means that it's a 1 by SC, it's a capacitor of what? 2 farad, all right? Whenever I say 3s, what do you mean by this? 3 into s or s into 3. It means inductor of 3 Henry. Am I right? Whenever I say S into CR square, what do you mean by this? It means it's an inductor of value CR square, right? So 1 by 2S means capacitor of 2 farad. S into 3 is inductor of 3 Henry. S into CR square, it's an inductor of value equal to CR square, right? So this is definitely an inductor, but its value is given by whom? The capacitor and resistor. So such a circuit is called a gyrator. So you can use this circuit to operate it as if it is an inductor. Whatever the frequency response an inductor will give you, the same frequency response is expected in this circuit also. close the door. Abhi. So inductors are bulky and power thirsty. So that's the reason we want to eliminate an inductor using capacitors and resistors, right? Okay, so how are we going to do this? If you do by KVL or KCL, it is cumbersome, right? Because there's a loop here, there's a loop here, there are 3 loops. Instead, you can either do by source transformation, or you can break the network for every 2 resistors with a voltage source. I've given you an equivalent, right? You can replace it by 1 voltage source in series with resistor. So that is much easier for you to do, right? So let us solve this by both the methods. So what if we have a 10K with 10K? We have 8 volt here. So what is source transformation? The source transformation tells you that 8, this is V and this is R. It is nothing but 8 by 10K in parallel with 10K. Eight by 10K in parallel with 10K, and the 10K still remains same. What is 10K parallel 10K? That is 5K. 5K. So this is equivalent to 8 by 10K in parallel with 5K. Now can I have source transformation here? This multiplied by this value is 4 volt in series with 5K. So you can have 4 volt in series with what? 5K. So this whole network, you can reduce it to 4 volt in series with 5K. Here again you have another 5K, 10K, and 3K. Right? So now what is 5 plus 5? 5 plus 5 is again 10. 5 plus 5 is again 10. Now, in the previous case, you had 8 volt, 10K, 10K. You got 4 volt with 5K. Now it's 4 volt, 10K, 10K. So what is expected now? This network, if you break it till here, it is going to be again 4 by 10K in parallel with 10K. There's again 10K here and 3K. What is 10K parallel 10K is 5K. So then 4 multiplied by this is going to be 2 volt in series with 5K and 3K. So what is 5 plus 3? 5 plus 3 is 8. So you have 2 volt in series with 8K here. See how simple the network has become now. This is an inverting amplifier. V0 is going to be minus R2 by R1 times 2. It is minus 1 volt, right? V0 is going to be minus 1 volt. So this is by what transformation? Source transformation. This is by source transformation. Right? Or you can do by the node method, but it takes, the number of equations are more, right? You can either do by Thevenin equivalent also, method 2. Now this is much easier. I told you there are so many Thevenin equivalents you will study in networks course, but I don't want that. I want only this simple Thevenin equivalent. if I have a voltage source V series with two resistors, what is the equivalent? The equivalent here is going to be the open circuited voltage between the two terminals, which is VThevenin, VOC. It is two resistors of same value, 4. And what is the equivalent resistance? You see from here, short the voltage source, 10K parallel 10K, going to be 5K. So this network till here, we are going to cut this till here. Till here, we are going to cut this and replace it with this network. So you have 4 volt in series with 5K. Here you have an additional 5K, 10K, and 3K. Now this 5 plus 5 becomes 10. What if I take this network separately? 4 volt with 10K, and then you have 10K here. This is equivalent to the open circuited voltage here, which is 2 volt in series with 10K parallel 10K, which is 5 till here. So now we are going to replace this with 2 volt in series with 5K, and here you have 3K. This is 2K. Now this is 8K, right? So this whole network is 8K. So what is V0? Minus 8K by 8K into 2. Is it 2? 2 or 1? What did I do here? 8K by 8K into 2 is 1. It is minus 2, right? Minus 2. Right? So however you do, your answer is not going to change. So you can do by source transformation, or you can do by Thevenin, or you can take two nodes here, V1 and V2, and then solve, or Vx and Vy and then solve. Doesn't matter. You can take virtual ground here, Vx, Vy, two equations you can solve, right? The point is, if such a big train is given, much larger, then it's unlikely that you would do it by nodal analysis, right? It's always better, or you can orally do it. So 8 volt, 10K, 10K, so you're going to get 4. 4 in series with 5K. 5 plus 5 is 10. 10 and 10 are there, you get 2. 2 in series with 5K. So final outcome is 2 in series with 5K. 5 plus 3 is 8. So 5 plus 3 is 8. 2 in series with 8, and then 8. Your V0 is minus 8K by 8K into 2. Your answer is going to be minus 2, right? So this is similar in your digital. It's some kind of an R2R ladder network, something like that, right? So first class, I've given you the Thevenin's equivalent, right? So note, first class, I told you if you have a voltage V, R1 and R2, you have voltage V, R1 and R2, this is equivalent to a single voltage, which is VR2 by R1 plus R2 by voltage division in series with R1 parallel with R2. You remember, there's something I have given you, right? my first introduction. So very handy. If you know how to do this, it saves a lot of time. Okay. Now, we know VCVS, what is the job of a VCVS? To have high input resistance, low output resistance with some gain, right? What if gain is 1? Gain is 1 is also called a buffer or voltage follower. Voltage follower, a buffer or voltage follower. This is a VCVS. A buffer or voltage follower. A buffer or voltage follower. Now, it is a VCVS with high input resistance and low output resistance. It is used as an impedance matching device. To connect high impedance source to low impedance load. So this is something we are going to discuss now. Very important. We have already done this in VCVS independent sources once again, because now there I have explained VCVS with a model, right? RN like that. Now we have a practical op-amp which does the job. It's used as an impedance matching device to connect high impedance source to low impedance load, right? So buffers are power boosters. With a large current gain. Right. And what is the voltage gain? AV. The voltage gain is approximately equal to 1. Right. So you have, this is Vin. What is this node here? This node is Vin. Here V0 is Vin. right? Or you can calculate like this. Your V naught by V in is going to be A by 1 plus A beta. So what is beta? Beta is a feedback factor. So you're feeding all that voltage to the input. So if you think that, if you say that, sir, I don't agree that this is Vn, it is some feedback voltage Vf. So your Vf by Vn is beta. Beta is Vf by V naught, which is 1. The same voltage is fed back here, right? Because through the wire, just a wire, it's a short, right? So you can say that this is V naught, but you can't say that that is V in, right? So it's the same wire that you're connecting. In such an occasion, what will be the gain? The practical op-amp gain is around 10 lakhs by 1 plus 10 lakhs. Beta is 1. Beta is Vf by V naught is 1 because of the wire that we are connecting here. So 10 lakhs by 1 plus 10 lakhs is approximately 1. 0.99999 something, right? So buffers have a voltage gain 1, they have large current gain, they have high input resistance, low output resistance. They are used for impedance matching to connect high impedance source to low impedance load. What do you mean by all this? Now, what is this story? Okay. So what do you mean by this? Now, let me give you a simple example. Suppose I have a voltage Vs. This transducer has some internal resistance 9K, right? Now I want to transfer this to the load here. This load is 1 kilo, 1 kilo. Because gain 1 is not a joke, right? To get gain 1, lot of deliberate effort is made in this circuit. You can see that. But what a student will think is, he has no respect for an amplifier with gain 1. He says, gain 1 is a buffer and it's not an amplifier. No. Anything that is a power booster, it's got power gain, is an amplifier. In fact, buffers are great amplifiers. Because a student, the first impression a student gets is, what is there in gain 1? You don't need it. You just connect it with a wire, you get the same output equal to input. So why do we need an amplifier? Suppose this is a wire that you're connecting, right? Suppose I have a wire here, right? This is a wire. Just, yeah. We're connecting the load and the source. There's a source in a box. And I have a load in a box. So what is the first impression a student will get? Just connect the source and the load with just a wire and you get gain 1. Now the question is, if you don't connect the load, what is the output? If you don't connect it, this voltage is going to be Vs. The moment you connect it with a wire, this voltage is going to be Vs into 1K by 9K plus 1K. This is Vs by 10, all right? Vs by 10, right? So where is that means only 1/10 of the signal has come here, right? So what happens, suppose you have, your friend is there, right, at the Ganpati Pappa Murti, there are 10 laddus here, right? So VS is like 10 laddus. And out of the 10 laddus, who is eating? Source himself is eating 9. Lord only 1. Are you getting? But what is gain 1? All the 10 laddus, all VS has to be transferred to the Lord with no attenuation. But who is eating 9? The source 9. You have 10 laddus at, right? The 9 portions are gone at the source and only 1 portion. So we need an impedance matching device, somebody who can cheat this, who has to show 9K don't eat, I'm going to snatch. And they have to transfer everything to 1K and say, 1K, just take all the 10 laddus. Just take 10. So how do we do this? To do this, to solve this problem, we have to connect it in this fashion. We have to take an op-amp here. And I told you this is V in and this is V naught. We know V naught is equal to V in. Here you have to connect, right? So here you have to connect 9K. And here you have to connect 1K. And now see the show. If you connect 9K to the op-amp, right? The op-amp, now you have 10 laddus here, VS, right? Op-amp draws no current. Op-amp draws no current. What is the current here? 0. Complete will come to op-amp. Your V in is VS. Now this 9K should only smell the laddus like that, right? So the complete laddus are now snatched by the op-amp. This is, these are for 1K, please. I want gain 1. I want all the VS to come to 1K. So I'm not going to give you, right? So he's nicely going to snatch. Now this fellow is just looking at the laddus, right? So just, he has to only smell. He just pass in front of him, just goes and stays at non-inverting. An op-amp with his power supply will generate the same laddus now to, this is VS, so this node is VS. He has to make much tastier laddus from the supply, right? So you want V naught equal to VS, exactly the same signal. You have to do, yeah, I mean, what is a model for this? What is a model for this? Let me draw the model for this. This is VS, this is 9K. 9K. What is the input resistance of the op-amp? This is 1K here, right? This is a op-amp box. Here, there is 1K. This is called impedance matching. I told you what is impedance matching. Before connecting the load, whatever the signal is there, after connecting the load, also the same signal. Now, if this is VS, now I have to write here V naught equal to VS. So it's a surprise, right? So you might start thinking, how the VS jumped from here to here? How did it come here to here? There's so many resistors in between. What happened? What happened? We did impedance matching. What is impedance matching? It's not matching of impedance. It is trying to connect an input resistance Rin, which is much, much higher than 1K. So op-amp input resistance, suppose it is 1 gigaohm. This fellow is in kilo, right? 3 zeros. This fellow 9 zeros. So he will not even smell, right? So this whole signal Vn is going to appear here. This is Rin. And what is op-amp's gain? The gain is going to be 1. The gain times of the input. 1 into V. And what is the output resistance of the amplifier? R0 is hardly going to be 1 ohm, right? So you see how good the amplifier is. He generates the same signal, but he's not taking, 1K thinks that he has to share the laddus with 1 ohm. And the gain is 1. So all the 10 laddus appeared here, all the 10 laddus, and the op-amp is saying, just you eat, right? So I'm giving you, I've generated them from the supply. I came to know from the input, right? And the 9K is just looking at the show. The whole signal is being snatched from 9K. But if you connect a voltage divider, what is happening if you just connect 9K and 1K here? Most of the signal is dropped in 9K. nothing is going to 1K, right? So this is called impedance matching. So what is impedance matching? It is to connect, it is to have an amplifier whose input resistance is much higher than the source. Your Rin should be much higher than Rs. The amplifier is voltage controlled. It is to have the output resistance of an amplifier much lesser than RL. Then the amplifier is a good voltage source. To have high input resistance and low output resistance, all the signal is now going to be transferred here, right? Okay. Now, just apply logic. Let's apply logic now, right? Okay, it's all the impedance matching stuff, you just keep them aside. Why we need an amplifier if you want the voltage gain 1? That is more important. Why do we need an amplifier? Just tell me logically, I have 10 volt, and this is 9 kilo ohm and this is 1 kilo ohm. Just for a simple example. Even if you directly connect it with no amplifier, what is the current that is going to be? 10 by 10K, it's going to be 1 milli. Now tell me, how can I have V0, this V0 is 1 volt. If V0 should be 10 volt, then current should be 10 milliampere, no? If 10 milliampere flows in 1K, that who will give that current, sir? The source itself is giving 1. That means it has to come from somewhere else. That's the power supply. There has to be an amplifier. Because you directly connect, you want it. How much current should flow through 1K to get 10? You need 10 milli. But the source, the maximum short-circuited current of the source itself is 10 by 9K. So it's in milliampere. 10 times of that, who will give? It has to come from an amplifier. It has to come, right? So in future, we are going to have circuits like this, right? Circuits like this. There's a common collector, right? For this common collector amplifier in future, it's an impedance matching device. We do the same thing here. We connect 9K with Vs, and I'll show you that it's going to snatch, because the base current is very small, it's going to snatch all the Vs here, and your V0 will be Vs, but this is generated from the supply. Its current gain is very large, right? So we will do all this later, but I'm just giving you an example, right? Just in future. So an impedance matching device is a device which connects high impedance source to low impedance load. If your source is having high impedance and your load is having low impedance, believe me, you will not get the same signal. The signal is going to get attenuated. To stop that attenuation, there should be somebody who does this trick, having a high resistance at input and cheat the 9K, get all the signal, and then the low resistance at output, right? See, I still remember when I was working for Wiproji Medical Systems, my manager, I was working on some board, some digital board. At pin 2, I was expecting a signal, right? There was some signal here at this pin. Now, my manager, he just came to me, he said, he's almost, I think, at that time, 55 years or something, right? Just after diploma, I joined Wiproji Medical System. I was not even a graduate at that time. And then I've done my MIT and MTech, so that's fine. But you know what trick he played? He came to me, I was working on that board, I was just observing the waveforms on the CRO, whether the circuit board is fine or not. He came to me, said, get me a glass of water. I said, okay, old man, right, 55 years. So my manager, I went and I bought a glass of water. I said, yeah, CR, we used to call him CR, C. Ramchandran. CR, okay, take this. And when I went there, he connected a worst load here, worst load, low resistance load. And then he said, is your circuit board ready? Yeah. Can you show me the waveform? The moment I took a probe and put it here at this pin, the signal is gone. The signal became this much. I felt that something happened. There was a signal here. I observed it. I put a tick mark. We had it, right? Everything is fine. But I just went, I came back, something happened, and then the signal is missing. It's got attenuated. And then he laughed, and then he said, try to figure out, right? Then I don't know whom to ask, right? There was one more friend. He was sitting beside me. I said, there was a signal, and now suddenly the signal is gone. It's become small. Then he said, maybe it's loading. I don't know what is loading, right? So I said, okay, loading. For whom to ask, right? And then that day I went home. I didn't sleep, so I just opened the book, loading L alphabet, and then came back. And then I realized that there was a buffer there in that diagram. To avoid loading, we need a buffer. The next day when I came, I connected a buffer here at this pin, right? And then I didn't disturb the worst load which he connected, right? Some sensor he connected here, right? And then I showed him there's a big signal here because this board, internal resistance, what is this board? You can say that the internal resistance of this board here is much, much higher than the source, right? But now the input resistance of this buffer is much, much higher than this. So complete signal will appear here. And this op-amp was generating from the supply the same VS. The next day I called my manager. He said, sir, please come, right? I know how to avoid loading, right? So, and then I brought back the same signal here, even with that load. But if you don't connect the op-amp and directly connect that load to that board, the signal is gone. But if you remove that load, you have a big signal. You connect it, something like you remove 1K, you have 10 volt. You connect 1K, it becomes 1 volt, right? So anytime, so that day I came to know that if I connect it, signal is gone. If I don't connect it, there's a big signal. That's called loading, right? And how do you avoid loading? Even if you remove the load and connect. Now, if you remove RL or connect RL or do whatever, the signal is always going to be rock solid. It's going to be VS. It's again going to be the same VS here. Because the buffer's input resistance is much, much higher. The buffer has a gain 1. His input resistance Rn is going to be much, much higher than Rs. And its output resistance R0 is going to be much, much lesser than Rn. This kind of a cheating, right, is called impedance matching, right? It's called impedance matching. So impedance matching means, right, so this is for voltage transfer. This is for voltage transfer. What about if you want to send current? current, voltage buffer, current buffer. Completely complementary picture you get. A voltage buffer should have high input resistance, low output resistance, with a voltage gain 1, with a large current gain, high current gain. And what is a power gain AP? AV into AI is approximately A, because AV is 1. Now tell me, if you want to take current from the source and give it with no attenuation, what you have to do? You should completely complementary to what you have written here, should have low Rn, high R0. Please, to understand this, go for the diagram CCCS. Go for the diagram CCCS, which I told you in my first class, right? We've already drawn for current buffers of CCCS in my first class. Low Rn, high R0 in dependent sources. Its current gain should be 1. It has high voltage gain. And the power gain, which is the product of voltage gain and current gain, is approximately going to be voltage gain. So in future, we are going to do again and again. These things we are going to do again and again, right? In a topic which is what amplifier? Common collector. Here, we're going to do this for a common base amplifier in future, not now, right? Just an example. So if you want high Rn and low R0, that means you're transferring voltage. Suppose if you have a buffer that's got low Rn and high R0, that means that buffer is going to take current, snatch all the current from the supply, and then give it, right? For that, in CCCS, you know you have to draw a Norton equivalent here, right? See, in the previous problems, when we have done the Thevenin equivalent and source transfer, please don't apply voltage division. Voltage division can only apply when the same current will travel, right? But because the current is getting divided, you are not allowed to apply voltage division, right? You can apply voltage division only when same current will flow through two resistors, right? So you can only do by the Thevenin's equivalent, or you can do by source transformation, or you can apply nodal analysis or Kirchhoff's KVL voltage law, right? Yeah. for the Miller integrator given, sketch V naught. Find Vc at t equal to 0.5 millisecond. Assume capacitor initially uncharged. Assume capacitor initially uncharged. This is a gate problem. Simple gate problem on Miller integrator. This is also a simple gate problem. Now the same problem, the same gate problem, I want to change it, right? So I just want to change the same problem. Excuse me. See, op-amp inherently is a VCVS with no feedback. But after giving feedback, the whole story changes. The whole story changes. Now, through non-inverting, you can have voltage control. Through inverting, you can have current control. At the output side, if you directly take the output, if you sample the output directly from the output pin, it is voltage. If you take through a load resistor, then it is current. So op-amp, 4 amplifiers we can design with 4 types of feedback, right? This we will learn in feedback amplifiers. In feedback amplifiers, what is series, shunt. Now, this op-amp inherently is VCVS, but after feedback, it can be VCVS, CCCS, VCCS, and CCVS. So the same VCVS op-amp can be used to build voltage amplifier, current amplifier, transconductance, transistors. We have seen all the 4 types of amplifiers in the class, right? They are all because of 4 types of feedback topologies, right? So when I draw a buffer, the buffer, why a buffer is a VCVS? Because it is having high resistance and the input is at low resistance. That is why. So in feedback amplifiers here, in feedback amplifiers, what is that I'm going to teach you in feedback amplifiers? In feedback amplifiers, I'll show you that if you want a VCVS, VC means high RN. VS means low RN. High RN means series, low RN means shunt, right? So this is something we are going to learn in which topic? Feedback amplifier. So if you still say that, how I want to know right now what is series and shunt, roughly I'm giving you, but this is a whole exercise we have to do here. So this is 9K and this is 1K here, right? 1K. Right? So now, what is beta here? Beta is 1, right? So this op-amp is an amplifier. Here we have beta 1. This is Rn. This op-amp equivalent. Here you have 1K. This is beta. Sorry. Oh my God. So beta is from here. So this is something we will do with this exercise. So here there is series topology and here there is shunt topology. So series means high resistance, shunt means low resistance. This is something we are going to do. For every circuit right now, we can't draw this, right? So I'm just telling you, non-inverting is for voltage, inverting is for current. But in feedback amplifiers, I'm going to specifically show that non-inverting, if you just opens up like this, right? So if non-inverting, naturally it becomes series. So this is something we will learn in feedback amplifiers. So not now. Are you getting? When I say it has high resistance, it's a VCVS because the input current is what? What is the current drawn by op-amp? 0. High resistance, current 0, it's almost like an open circuit, high input resistance, right? So slowly I'll show you that the input resistance is multiplied by a factor 1 plus GH and the output resistance will decrease by 1 plus GH. So it's something in future we will do it, right? So not everything, because this is a separate topic, feedback amplifiers, right? In future. So not now, right? Okay. So now the overall input resistance is, so now you can say that the overall input resistance is here. The overall, because some students in the comment section, I'm seeing that, what is this Rn? It's the op-amp input resistance multiplied by 1 plus GH. So if the op-amp already input resistance is 1 giga ohm, multiplied by 1 plus G is 10 power 6, 1 giga into 10 power 6, smell also will not be there through 9K. This is not the op-amp's input resistance, the op-amp's input resistance, but the feedback together of 1 plus GH multiplied. That's a very big number. This is not 1 ohm, it's going to be 0.00001. Are you getting? So how do we calculate this? We are going to do this exercise in a topic called feedback amp. For right now, first of all, we should know what is voltage control, what is current control, what is high resistance, what is low resistance, what is virtual ground, how do we keep applying virtual ground and solving problems. So we have covered a basic, what you call, adder, subtractor, differentiator, integrator, like that, right? So in future, we are going to unwind that and solve. Okay. So don't worry about that. So step by step, we will go. Yeah. For the Miller integrator given, sketch V0. Sketch V0, right? The capacitor is initially uncharged. Capacitor is initially uncharged. So now, what is a Miller integrator? Once again, let me repeat it. What's an integrator? When a constant current flows through a capacitor, it charges linearly. It charges linearly instead of exponential. Instead of exponential, it charges linearly, right? So when it charges linearly, please, you cannot apply VC0, VC infinite, e power minus t by tau. No, you should not apply, because I'm having a constant current, I, and this constant current flows through a capacitor. What is the voltage across a capacitor formula? The voltage across a capacitor formula is 1 by C integral I dt. Now, please help me with the integration. What is integration of exponential? If the current is exponential, integration of exponential is exponential. So if your current is exponential, your voltage is exponential, right? That will happen in an RC network, simple RC network, no op-amp. But when you have an op-amp, you are having virtual ground here. See here, there's a virtual ground. The current I is going to be V by R, constant. Now tell me, what is integration of constant? Integration of constant is what? Integration of constant is a ramp. Because in integration, in mathematics, you have studied that if you have a constant, you can remove it outside the integral. Can I remove it out? Right? Can I remove out? I can write I by C. What is integration of dt is t. This capacitor, please don't apply e power minus t by tau. This capacitor, for the first time, is obeying a formula y equal to mx. What is y equal to mx? It's a straight line passing through the origin, right? The capacitor is going to charge linearly. And what is the slope m? It's going to be I by C. I repeat, capacitor is going to charge linearly only when the current is constant. If you want a constant current, you can give a voltage source with a resistor, right, through the inverting terminal of an op-amp. The op-amp can simulate a current I equal to V by R. The same current keeps on flowing through the capacitor. The capacitor is forced to charge in a linear fashion. But in a simple RC network, the current is exponentially decaying, right? The voltage is exponentially rising. Because then you can characterize that exponential waveform with a plus b e power minus t by tau. I proved in my first class, right? Then I told you it's VC0, VC infinite. Don't do that. Don't do that, because by looking at that switch, you just go and apply that, right? VC0, VC infinite. No, don't do that, right? If the current is always constant, you should never apply. But the current, only a resistor, capacitor, and a voltage is there, then it's going to simulate a first order differential equation. There you can apply, right? So only RC, then you can apply. So here the current is exponential, but when the voltage is going to be exponential in this circuit. In this circuit, suppose I'm having V here, R here, T here. As the capacitor voltage increases, the current will keep on decreasing. Here the current is going to be this and the voltage is going to be this, right? But not with op-amp. right? Not with op amp. Okay, so let's solve this problem. What is I here? What is I? I is going to be V minus 0 by R or V by R. V is constant, R is constant. What is constant by constant? Constant by constant is constant. Now, if this is I, this is also I. You can take some polarities like this. What is capacitor polarities? If at all you want to take, what's the discipline? If you have a capacitor like this, current always flows from higher potential to lower. So you can take the polarities like this, all right? So what is VC? VC equal to 1 by C integral I dt. Because current is constant, it is I by C of t. I is nothing but V by R, V by RC of t. The capacitor is going to have Y equal to mx, Y equal to mx. Constant current, right? Now, what is V naught? What is V naught? You have a capacitor here. We see the output node is V naught. This is virtual ground. So VC equal to 0 minus V naught, or V naught is minus VC, which is minus V by RC of t. Your V naught is going to be minus V by RC of t. Am I right? Yeah. So what is I? I equal to V by R, constant. So integration of a step function. This is a step. Integration of step is going to be ramp. The slope is V by RC. And what is V naught? V naught is minus VC. Slope is minus V by RC. Now, how long does it move? I mean, no supply is given. It'll go, one will go to the sky, the other will go to the ground, right? But if there is a power supply limits, then it's going to saturate at some point. It's going to move like this till op amp saturates. Till op amp saturates. My hand shivers. Age problem. I can't draw a straight line. Oh, okay. Till the op amp saturates. Fine. So with this simple formula, we can easily solve the get problem here, right? Now tell me, if this is 10, what is the voltage at inverting? 10. Vp equal to Vn equal to 10. All right. So you can take a current I, this is I, this current is also I. I equal to 0 minus 10 by 1K. minus 10 milliamp. Minus 10 milliamp. And what is VC? Let me see the polarity. Same. See, what if the current is in the opposite direction? Suppose your assumption is in the opposite. You can assume, I told you, whatever way you want. But if you assume the opposite direction, right, minus VC equal to 1 by C integral IDT, right? So VC equal to 1 by C integral IDT. So the time is 0.5 milli, so it's I by C of t minus 10 milli by 10 power minus 6 into 0.5 milli, it's minus 5 volt. The capacitor is going to charge to minus 5. And what is V naught? What is V naught at that point? V naught. This is VC, V naught, 10 volt here. What is V naught? VC equal to 10 minus V naught. 10 minus V naught. Minus 5 equal to 10 minus V naught. Your V naught is going to be 15 volt. So imagine the op amp is not saturated, 15 volt, because no supply is given, right? Okay, so one more gate problem, a simple gate problem. If this is ground, this node is at 0. Vp equal to Vn equal to 0 volt. Op amp draws no current. What is the current I flowing? I equal to 5 minus 0 by 1k. It is 5 milliampere. All right. So what is Vc? 1 by C integral IDT or I by C of t. So Vc equal to 5 milli by 10 power minus 6 into time 1 milli. So it is going to be plus 5 volt. Vc is plus 5. So what is V naught? Vc equal to 0 minus V naught. Your V naught is going to be minus Vc, which is minus 5. Now, did I tell you that whenever a supply is given, what is the first step that you have to do? What is the first step you have to do? Should we calculate or draw the transfer characteristics and then calculate? Yeah, tell me. The first step you have to do is, if this is Vd and this is V naught, you have to see what is the transfer characteristic. Your output can lie between minus 10 and plus 10, right? So is your V naught between minus 10 and plus 10? Yes, yes. V naught lies between minus 10 and plus 10 volt. Therefore, V naught equal to minus 5 volt is true. So when you take Vd0, your V naught should be between minus 10 and plus 10. So your V naught is minus 5, is true, right? Now, the same gate problem, I have changed this. I have changed it. I mean, what is the only change that I have done in the previous? You can see that the whole diagram is same, so I don't have to calculate. I only changed it to how many milliseconds? 3 milliseconds. So what will be your VC? What will be your VC? Your I is going to be 5 minus, this is already calculated. Once again, I'm just writing 5 milliamp. And VC is I by C of t, 5 milli by 10 power minus 6 into 3 millisecond. This is going to be 15 volt. Your V naught is minus VC is minus 15. Minus 15. Now, what is the transfer characteristic? It tells that your output cannot lie between minus 10 and plus 10. So minus 15 is false. False. It's not possible. It is not possible. Therefore, op-amp has saturated at V naught equal to how many volts? Your V naught is negative, right? So your V naught is negative. So input is given to minus terminal. So this time, is he going the positive direction or the negative direction? Negative. So your V naught could be minus 10 volts. Your V naught is minus 10 and your VC is going to be plus 10. Plus 10, right? So I've just changed the gate problem, right? I increase the time to 3 milliseconds. So I want to show you that this circuit, the VC or V naught, what is V naught? V naught is minus 10. So it starts with 0, goes there at 1 millisecond. At 1 millisecond, what is the voltage at 1 millisecond? In the previous example, at 1 millisecond, it would have been 5 volts. At 2 milliseconds, what if I put 2 milliseconds here? 2, right? So 1, 2, 10, right? 10, 2 milliseconds, maybe minus 10. And after that, it would have saturated. So even at 3 milliseconds, it is still at what value? Minus 10, right? Okay, so shall we take a break or something, right? I'm a little hungry. Okay, so when we come back, we'll give a pause to op-amp because nonlinear applications like the log and exponential amplifier, you can cover only when you have diode. So we're going to give a pause for linear applications, and after the break, we are going to start diode applications like simple clipper, clamper, peak detector, right? And then we have to combine op-amp with diodes, right, to have precision circuits. So even op-amp has rectifiers, peak detector, half wave, full wave. Op-amp will also have, right? But you cannot directly go to op-amp now and do half wave, full wave, because we have not introduced simple diode circuits. So diode, one resistor, small, chota circuits we have to do. And then if you combine it with op-amp diodes, then it's much easier. By looking at the circuit, by inspection, you can tell whether it's half wave or full wave or what sort of circuit. Are you getting right? So we will have to spend some time on simple diode problems. One diode, one resistor, like that, right? we'll get habituated, and then we can go for non-linear application. So after the break, we are going to see simple diode circuits, right? Take a break. Okay, can you hear me? Can you hear me? Yes, thank you. So the topic is diode applications. So what is that we are going to cover? We're going to see simple diode circuits, clippers, peak detector, clampers, voltage multipliers, and of course, rectifiers. Simple diode circuits, clippers, peak detector, clampers, voltage multiplier, and rectifiers. Right? So these are the topics we are going to cover. Simple diode circuits, clipper, peak detector, clamper, and voltage multipliers. Now, what is a diode? A diode is a two-terminal non-linear passive device. A diode is two-terminal, non-linear, passive device. Now, how do you check whether a device is linear or not? How do you know that the device is non-linear? So many ways, but a simple test is think about it. How do you check whether a device is non-linear or not, or linear or not? To check whether the device is linear or not, a simple test is if I double my input, my output should also get doubled, right? Doubling of the input signal should produce doubling of the response. So if I double my input, my output should also get doubled, right? So the doubling of the input signal should produce doubling of the response. So that's linear. Passive, active. How do you know whether a device is active or passive? For active device, when do you say that a device is active? There should be a built-in source of power. So that means there should be an input, output, and the third terminal, you have to have a power supply. But diode does not have that option. It has an input, output, that's it, right? So it's just two terminals. It's a two-terminal device, passive, right? But if there is a built-in source of power, so for the built-in source of power, I told you, for the input port, output port, there should be one terminal for the power port also, right? So there should be a built-in source of power, right? So that means generally three terminal devices. So generally three terminal devices are active devices, right? So unfortunately, these two things diode doesn't have. If you double the input, the output will never get doubled. Please don't expect the linear variation like a resistor, right? So that's not going to happen. And diode has only two terminals, so there is no extra terminal to connect the VCC supply or whatever you call it, right? So devices that have VCC supply, a built-in source of power, they are active devices. So diode does not have any of them, right? It's a nonlinear active device, sorry, passive device, right? Okay, so now we're going to treat this diode as a black box. As a black box, we are not going inside the device, right? If you go inside the device, what is the problem? If you don't choose the element boundaries very carefully, and if you go inside the device, what is the problem? If you go inside the device, then you have to deal with the charge and the depletion inside. Instead, if you choose the element boundaries very carefully and jump from anode to cathode, right, from anode to cathode, and treat the whole device as a black box, then what is the characteristics of the diode, right? So if you connect a diode to some source here, then how do you draw the characteristics between VD and ID? VD and ID. If you take VD on x-axis and ID on y-axis, it's almost here, right? Now, what is the relationship between the current and the voltage? So that with the help of this diode, we are going to create applications. So this is a design course. It's not a device course, I told you. Every device is treated as a black box. We don't want to know what happens inside, but we definitely have to inspect what should we do with the terminal behavior, with the at the port, right? So what is VD and what is ID? See, simple. The day you have decided to apply Kirchhoff's laws, you are not allowed to go inside, because what does Kirchhoff's law tell you? Suppose you have a bulb here. Kirchhoff's law tells that this is entering current, this is leaving current, right? If you say entering current minus leaving current is always charge buildup, right? So if you go inside the device, then you have the conductor, dielectric, boundary condition, all that stuff, right? But if you choose the element boundary very carefully and you jump from here to here, from the anode to the cathode, then the Kirchhoff's law allows you to make dq by dt as 0. Then the current entering is equal to the current leaving. This is KCL. So please, the day you're applying KCL, you have neglected what is happening inside the device, because you go inside the device, entering minus leaving, dq by, we don't want. What is a diode current? There is no entering current, leaving current. ID, that's it. Diode has a current ID, that's it. No entering, leaving, nothing is there. ID. What is the voltage? VD. Right? So you will allot a unique voltage, unique value of voltage to a device, and you will allot a unique value of current. Every device we are going to do this. If you allot it, then you don't have to go inside. For example, a transistor is there. It's a black box. The day you say this is IB, IE, IC plus IB is IE, that's it. You don't have to go inside the device. Because if you go inside the device, then your IE equal to IC plus IB will fail. There has to be an additional term dq by dt, right? We don't want that. So we have to choose the element boundaries very carefully. You don't have to go inside. You have to jump from the anode to the cathode, treat the whole device as a black box. That's it, right? There's only one current. We allot a unique value of current. Okay. What is the relation between ID and VD? Very simple. You all know this. ID equal to A e power BVD. All right. A e power BVD. What is A? Where A is I naught or IS, which is the reverse saturation current. Reverse saturation current. Its typical value is around 10 power minus 13 ampere, right? Now all this we should not consider when we're doing clippers and clampers, right? Some constant A. What is B? 1 by eta Vt. And Vt is Kt by Q, that's thermal voltage. It is around 26 millivolt or 25 millivolt. Right. So if I consider all these constants and then ID and VD relationship, I may not be able to solve a 3 diode problem, 4 diode problem. It becomes very, very cumbersome, very, very difficult to do, right? So ID is A e power dVd. And you know what? When I look at this equation, this equation is a little misleading. The reason is, now just tell me in this equation, who controls whom? Who controls whom? Do you think VD controls ID or ID controls VD? Who controls whom? I mean, I just want to know the answers from you, right? Who controls whom? Do you think VD controls ID or ID controls VD? Who controls whom? Who controls whom? Who controls whom? Do you think VD is controlling ID or ID is controlling VD? Who is dependent on whom? Okay, so let me write this in this fashion. ID equal to IS into e power VD by VT. For simplicity, eta is 1. So by looking at this equation, who is controlling whom? If you say that ID is being controlled by VD, that means a small change in VD will create a large current ID. Is it true? What if I write this equation in this fashion? VD equal to, if I send the IS to the other side, it's ID by IS, and VD is VT log ID by IS. Now you tell me, I can write the equation in any way I want, right? But who is controlling whom? Who is controlling whom? Is VD controlling ID or ID is controlling VD? Okay, now most of you have said that it's a VD which controls ID, right? That means what? You want to stick to the conclusion that a small change in VD will create a large current ID. Or is it true that however the current keeps on changing, the voltage drop across a diode will not change much? It's a logarithmic device. It's a 0.7 volts, 0.7, 0.69, see here, the characteristics, if you see, which is true in this characteristic? Do you think in this characteristic, however the current changes, the current keeps on increasing, however the current changes, the voltage is not going to change much. It's almost 0.7. So I can use it as a switch. Is it true? Or do you think that a small change here, if I create, I'm going to get a large current ID, so it's an amplifier. Why I'm saying this is, BJT also has the same equation. This is VB, and this is connected to a power supply here, VCC, and your IC. What is the relationship here? Your IC equal to IS into e power VB by VT. The diode equation is also same, but please, diode is not an amplifier. It's just a switch. For BJT, if I take VB on x-axis, IC on y-axis, and I draw, it looks like the diode circuit, the diode equation. But who controls whom? Who controls whom? If I apply a small signal here, if I apply a small signal Vin at this point in the active region, near that 0.7, then I'm going to get this big output. Now I told you from where this output will come. It's not a magic, right? This output should come from the supply, from VCC. So BJT is an exponential device is true. But diode is a logarithmic device. So what do you mean by logarithmic? However, the current keeps on flowing, a large current, the drop across the diode will not change much. The diode says that you send me any amount of current, I'm almost 0.7. I'm almost 0.7 volt. You can use it as a switch for a diode. But BJT is what device? Exponential, because there is a built-in source of power. Now, if you don't believe me, that there'll be a point where in future, not now, in future, just see, whenever I write in future, what do you mean by that? It means that I want students to think about it, think and just keep it aside. I would be explaining them in future, right? So see, the beauty is always in the process, not final answer, right? So you just keep thinking. So in future, I'll show you that I'll connect a logarithmic device to an exponential. Well, that will be more fun, right? What happens if I take a log device and connect it to exponential? Then I will cancel the nonlinearity. I can get the same current here. Because in a logarithmic device, the current will control the voltage. In the exponential device, it's the voltage that controls the current. So in future, I'll take a diode and connect it to a BJT. I will have the same transmission of current. That's the mirror. That's a current mirror. So in future, I'm going to take a diode. How do I create a diode? I short one junction in the BJT, right? In future, not now. And then I give the current I. This diode, because of the current, it gives voltage V. And that voltage, I'm going to pass it here and then build the same current. If these two devices are on the same IC, an integrated circuit, same beta, same everything is same, then this current, the reference current, the copy current is going to be the reference current here. Not now, not now. Just think about it, right? Just think. Diode is not an exponential device. It's a logarithmic device. However, the current changes, the voltage drop does not change. But BJT is not that. Even if slight change VB, boom, there's a big IC changing. That large current diode cannot give because there's no supply. Diode has only two terminals from where the extra current comes. There's no provision in the diode. There's only one current flowing in that loop, right? Okay, just think about it. Because I like this equation in a diode, but nonetheless, we always apply this equation. But I would feel that this equation will explain more about a diode than this equation, because it's customary that we always take voltage on x-axis and current on y-axis and build an equation, right? But to me, the y-axis is actually the input and the x-axis is actually the output when it comes to a diode. When it comes to a diode, because only two terminals, the current keeps on changing. See, a load is current driven. Because when you see the data sheet, right? If you see the data sheet, IN 4007 diode, the manufacturer mentions at least 0.1 milliampere or 1 milliampere should pass through the diode to break the barrier and give 0.7 volts, right? So the data sheet gives this much current should pass, then the barrier is going to break and it drops a voltage, right? But for all gate problems, what do? We say that a diode is not current driven, it's voltage driven. So you apply any voltage more than 0.7, the diode is going to take 0.7 volts. Are you getting? So this is something we are going to do now with problems. But remember, who is the input to the diode? Is a current. And however you keep current flowing, the voltage drop in a diode does not change much, right? Okay, right? So this is in future. So don't worry about this now, right? It's in future, not now. Not now. It's just a motivation. When I say in future, you just keep them aside and do the thinking, right? Okay. Now, how do we solve diode problems in a simple fashion? Now, if you can see here, in the diode characteristic, in the diode characteristics, Now here you have the microampere region. This is microampere, and probably here you have milli here, right? 1 milli, 5 milli, like that. But this is the microampere region. Now, what is micro? Micro is 10 power minus 6, right? 10 power minus 6. Now, what if I neglect this curve? We just want to neglect this curve. We just want, because microampere is very, very small. What if I can convert the diode characteristics like this? Like this. Otherwise, you'd say that, Sadi, this is actual. Right? So this is actual characteristic. And this region happens to be microampere, which you can neglect. So if I can convert the diode characteristics with straight line segment, what is the advantage? The advantage is, just now one of the student has given here the comment saying that can we apply superposition theorem to a diode, right? So it just says, can we apply superposition theorem, right? Diode is a nonlinear device. Superposition theorem is linearity property, right? Yes, diode will allow you to apply superposition provided you convert the diode characteristics with straight line segments. And when you convert them into straight line segments, you should operate at only one segment at any given time, right? If somebody tells you, show me the diode characteristics in analog. In analog, you should say that diode is this, or diode is this. They say that if this is the diode, it is a simple, right? It's a simple voltage source, 0.7 volts. We have applied 0.7 volts for voltage sources. We have applied superposition theorem. So I can apply superposition theorem even to a diode, provided I work only at this segment of the characteristic. Now, what if the diode fails in this segment, like we have done with the op-amp? We go back to the second segment and say that, no, sorry, my diode is not this, my diode is this. And then again, it allows you to apply superposition theorem, Thevenin, Norton, all the linear analysis that you have studied in networks course. So if you want a complicated diode, a highly nonlinear diode, to obey superposition theorem, then the diode should be replaced by these two segments, Either this, if it fails here, this. If you can do so, then the diode, which is highly nonlinear, will allow you to apply superposition theorem, Thevenin, Norton, right? So what is the summary of this discussion? So note, solving nonlinear equations is difficult. Solving nonlinear equations is difficult, right? How? Let's do DC analysis first. DC analysis. So what is DC analysis? Let me take a diode and give it to some DC voltage, VR, VD, and ID. Why diode problems are so difficult if you take the diode as nonlinear? Now, let's apply KVL in this loop. If you apply KVL, what do you get? First equation, ID equal to AE power BVD, nonlinear equation. But what is ID here in this loop? What is ID? It is V minus VD by R. So this end is V, this end is VD, ID is flowing, V minus VD by R. So from 1 into a e power bvd equal to v minus vd by r. Just tell me, how do you solve this equation? Now, the first impression which I got, because when we were studying this in first year, right? Numerical methods were not introduced by then. And then we started applying log on both sides. So what's the fun if you apply log on both sides? Log goes here, but the log comes here at the right side. And again, you have to apply exponential on both sides. So solving these kind of equations are difficult. It's very difficult. And anybody who solves them will have a name behind it. What are the big names who have solved this equation? Newton, Raphson, right? Gauss, Seidel. They're guys who have solved these equations, right? So these, or you can solve by trial and error. You can solve by trial and error, or you can solve by some numerical methods. Then I took the help of some math lecturer. I think he solved this by Newton-Raphson method. So with Newton-Raphson, he came to a conclusion that the diode voltage was some 0.7024, something like that. Then I said, why 0.7024 to get that? Because in other problem, when you try to solve, you're getting 0.7015. In one problem, you get 0.7024. In another problem, you get 0.70. So anytime you solve, the diode voltage is almost 0.7. Then we can start thinking, right? What if we assume 0.7? We can avoid all this analysis, right? What if we assume? So everything comes with an assumption. Otherwise, what is a op-amp characteristic? Op-amp characteristics, if you see, op-amp characteristics is a tan hyperbolic curve. Can I take tan hyperbolic equation and then solve an adder circuit? Very difficult. But we came to know that this line, because of high gain, is almost on y-axis. Then we thought that why not make an op-amp as piecewise linear? What is piecewise linear? It's linear piece by piece, portion by portion, segment by segment. So the diode that is highly nonlinear, we are going to convert that diode into piecewise linear. What do you mean by piecewise linear? Taking one segment at a time, we will solve. Either forward bias. If he fails in forward bias, go for reverse bias and solve. It's very, very simple, right? So we will solve diode by how many steps? 2, right? In fact, only 1. Because if he fails to be in forward, automatically we know he's reverse, right? Okay, so let me write it again. Note, what did we write before? Solving nonlinear equations is difficult. Therefore, the diode characteristics is approximated with straight line segments. Straight line segments. This method of analysis is called piecewise linear analysis. Piecewise linear analysis. Solving nonlinear equations is difficult. Therefore, we approximate the diode characteristics with what? Straight line segments. This analysis is called piecewise linear analysis. Piecewise linear analysis. Right? So now solving diode problems is extremely simple. From more difficult, we are jumping to very, very simple now, because 90% of gate problems is on what diode? Ideal diode. And see how simple the diode characteristics is. The diode characteristic, even if I neglect that 0.7, is going to be just here, right here. So now you have to operate either at 1 or at 2, but don't cross over the segment. Don't do half problem in segment 1 forward bias and another half in reverse bias. Then because of the discontinuity here, the diode is nonlinear. It will never allow you to apply superposition. If you are only in forward bias and replace a diode with short circuit, then it is just as if there is a closed switch there. Diode will allow you to apply superposition. What is this first segment? What is the equation of a line on y-axis? On y-axis, VD equal to 0, then your ID is greater than 0. VD equal to 0, your ID is greater than 0. What about the second segment? ID is 0 when VD is less than 0. ID is 0, current is 0 in second segment, voltage is 0 in first segment. So what is the equation of a y-axis? X equal to 0. What is the equation of x-axis? Y equal to 0. I mean, this is something you have studied in coordinate geometry, right? Maybe in your 10th standard, this x-axis, y-axis, right? So what is this equation now? This equation tells that, what is this equation? This equation tells that x is 0, right? X is 0. But when x is 0, your y should not be less than 0 because the segment ends here. Y is greater than 0. If x is 0, your y is greater than 0. What about here, this segment? This segment. Here, y equal to 0 and your x is less than 0, negative, right? So see, a complicated nonlinear equation has become very, very simple, child's play. This is a diode. and 90% of gate problems are on this. So now you tell me, how do you solve diode problems now? If VD is zero, what do you mean by voltage zero? What do you mean by voltage zero? The diode is replaced by short circuit. Current zero, what do you mean by current zero? Current zero means open switch. Voltage zero means short. I told you, right? So how do you solve diode problems? VD equal to zero when ID is greater than zero. If ID equal to zero when VD is less than zero. To solve diode problems, what is the procedure? What is the procedure to solve diode problems? What is the procedure to solve diode problems? Right? So if it has to stay on one segment, you have to make an assumption. What is the assumption? VD zero. When do you say VD is zero? If you replace diode by what circuit? Short circuit. So procedure says that replace diode by short circuit. Short circuit. That means your VD is zero. It's understood that VD is zero. Replace diode by short circuit and calculate ID. If ID is greater than zero, then diode is forward biased. The diode is forward biased, right? So when do you say that a current is positive? Current always flows from higher potential to lower potential. So when you say current positive, it is understood that the diode is what bias? Forward bias. Or what is the other definition of forward bias, which I will tell you later, right? Current is positive. That means current flows from higher to lower. Diode is forward bias when anode is higher potential and cathode is at lower potential. So what is the second segment? The second segment says that, see here, how do you solve diode problems? Current is zero. When current is zero, the diode is replaced by what switch? Open switch, right? The second procedure is replace diode with open switch. Replace diode with open switch, right? That means ID is zero. And calculate VD. If VD is negative, then diode is reverse biased. The diode is reverse biased. So please, for reverse bias, we have to prove that VD is negative. But you might say, sir, what if VD is positive? Then of course the diode is what? Forward bias, right? Or anode should be at higher potential than cathode. So how did we get this idea? We don't know about a diode. We came with this idea of solving simple diode problems from the characteristics. The characteristic says that if you use this technique by replacing a diode with short and calculating ID, if your current is positive, then the diode is forward bias. If your voltage is negative, when you replace diode with what switch? Open switch, then the diode is what bias? Reverse bias. Now, similarly, the second segment. What if the diode characteristics is like this? Some books say this is a practical diode. This is a practical diode. Practical diode. Tell me, first segment says that if VD equal to 0.7, replace the diode with 0.7 volts, then your ID should be greater than 0. For if ID equal to 0, which is an open switch, your VD should be less than 0.7. First segment assumption is voltage, findings are current. Second segment assumption is current, findings are voltage. Please don't assume voltage and then find voltage. The people will laugh, is it not? If you say let X equal to 2, what is X? X, if you assume X, you have to find Y. If you assume Y, you have to find X. If you assume voltage, find current. If you assume current, then find voltage. Are you getting? So if VD is 0.7, then you have to find ID. If your ID is 0, then your VD should be less than 0.7, right? In my first class, we have done this problem. Do you remember? This problem. The slope M is I by V, say, which is 1 by RD. In the first segment, the diode is replaced with 0.7 volts in series with resistor. Find ID. In the second segment, ID is 0, so diode is replaced with open switch. Find VD and prove VD is less than 0.7. Find ID. Find ID. Right. So you're right, if VD is less than 0.7, then the diode is what bias? Reverse bias. So this is for forward bias condition, for reverse bias. So it's forward bias. So now you tell me why diode will allow you to apply superposition theorem. Suppose I have a network like this, and here there was a diode. Here at this point there's a diode. Now you replace it with open switch or short circuit. Any Any network will allow you to apply what theorem? Superposition, right? Because there is no longer a diode in the problem. Similarly, you can apply superposition theorem when a network is like this. Can apply superposition theorem to diode circuits, provided they are treated as piecewise linear. So you should always operate only at one segment. Suppose you're doing forward bias condition, and you're doing reverse bias condition. Forward bias, you calculate the current here. If the current is positive, the diode is forward bias. So once it fails, you jump from here to reverse bias condition. So diode will allow you to apply what theorem? Superposition, because there's no diode in the circuit, first of all. Its equivalent circuit has come, its equivalent model has come, which is used in linear circuits. Now you tell me, won't you use 0.7 volts, 0.5 volts, 8 volts, 9 volts in linear circuits? Won't you use closed switch, open switch in linear circuits? But diode is non-linear. It is converted into linear elements like switch, closed switch, open switch, 0.7 volts, 0.5 volts, 0.6 volts, 1 volt, 3 volt, 5 volt, right? So when you replace them by voltage sources and switches, the circuit will allow you to apply superposition and Thevenin and Norton, right? All the linear methods you have studied in networks. I'll tell you a simple thing here. Digital circuits are non-linear, but they will allow you to apply superposition theorem. How? Suppose if I have a NOT gate, and for this NOT gate, if you write here X and say what is Y? Y is X bar, right? If you say Y is X bar, then it is non-linear. Because when you draw the characteristics, then the characteristic says that this can be either as logic 0 or logic 1. It's non-linear. You're crossing over the segment. But how can I convert a digital circuit into linear? How to convert to linear? So to convert to linear, if I want to convert it to linear, what is the discipline? The discipline is you have to work at only one segment of the characteristic. That means anytime you find a NOT gate, don't write X, write 1. That's it. Or 0. Don't write 1 or 0, right? Because you will cross over the segment. If you write 1, you will always have 0 here. Then you will work only at this segment of the characteristic. Then the characteristics of digital logic circuit is this. That's all. There is no other line. But if I change this to logic 0 here, you have logic 1, then the characteristic is going to change here like this. Here. This is gone. This is gone. Only here. So you are working at this segment or this segment. You're not working at the other segment. So the digital logic circuits, which are highly nonlinear, will allow you to apply superposition. And you will see in your VLSI course, the same NOT gate you can draw with a PMOS and an NMOS, right? If you draw with PMOS and NMOS, you can replace the PMOS, the QP and QN. You can replace them by resistors, the saturation resistors. And when you solve networks like this, when you solve them, you can apply superposition theorem. You can apply superposition theorem to a highly nonlinear digital circuit. What's the discipline? Don't write X, write either 1 and solve the whole circuit. If it fails, after some answer that you get, keep them aside, then have another logic 0, and then the output is 1. So even digital, analog, that is why superposition theorem, Thevenin, Norton, KVL, KCL, they are foundation of electronics, right? So they become founded. KVL and KCL, especially KVL and KCL is a workhorse, right? So this is very, very important that a student knows how to apply Kirchhoff's voltage law and Kirchhoff's current law, right? So now tell me, can we apply superposition theorem to a diode? The answer is no, you cannot apply, right? Because it's nonlinear. But how to solve diode circuits using superposition? You have to approximate the diode characteristics with straight line segments. This method of analysis, and you have to work at only one segment at any given time, not both the segment. Don't cross over the segment. Don't jump from here to here. Stay in forward bias. Keep on solving the problem. Solve. What is there? You have to calculate the current. The current is positive, fine. If the current is negative, say, sorry, diode, I thought you are forward. Now you're not forward, you are reverse. So draw another circuit, replace a diode with open switch and solve. While solving, if you think the network is very big, you can solve by Thevenin and superposition and Norton. But the diode is not a diode anymore. It's an open switch in second case. Or the diode is a short circuit in first case, right? So this way, diode problems are extremely simple in analog. In EDC, when you look at the diode circuit, diode equation, it just blows your mind, right? You can see the equation here, right? ID equal to IS and eta VT, and the reverse saturation current, thermal voltage, KT by Q, Boltzmann's constant, whatnot. If I keep thinking all of them, how can I solve a clipper problem or a clamper problem? But when I solve a clipper or a clamper problem, my diode is going to be very, very simple. He's either a short circuit or an open circuit for me, right? Short circuit, if I do what analysis? Short circuit, if I do the forward bias analysis. Open circuit, if I do what analysis? Reverse bias. So that way, diode problems are extremely easy to do, right? They allow you to, there is no need for you to apply nonlinear methods like the Newton-Raphson method. But once you should apply, right? In college, once you have done, you'll really enjoy the piecewise linear analysis. You'll feel, oh, diode is so simple. You find a diode, you just replace by 0.7, calculate the current. What's a big deal, right? Just apply one small Kirchhoff's law, right? Calculate the current. If the current is positive, your analysis is correct. If it fails, then you have to replace the diode by what switch? Open switch and do it. Are you getting? So this way, diode problems are simple, very, very simple. So whenever you find a circuit like this, so you have to solve them either by this method or by this method, right? So if you solve by this method, it's called the forward bias condition. If you solve by this method, you call reverse bias. So the diode is replaced by a short circuit or an open circuit. It allows you to apply superposition theorem, Thevenin and Norton. Okay, so I'll give you a simple example here. if you are asked to find ID, if VD on and the diode is on, you can take how many volts? 0.7. If VD on is 0.7. Okay, so our analysis always start with an assumption, right? So what is the assumption that we are doing? We will replace the diode with 0.7 volts, right? Or you can have a diode like this and just write what is a drop here? 0.7. So the diode has a drop of 0.7. What is ID? ID is simply going to be ID in this loop, right? So you can write KVL. What is KVL? -2 plus ID into 1K plus 0.7 equal to 0. So your ID is 2 minus 0.7 by 1K, which is 1.3 milliampere. Now, is ID greater than 0? True. That means diode is what bias? Forward bias. If the current flowing through the diode is positive, then the diode is what bias? Forward. So you can see here in the piecewise linear segment, if VD is 0.7, your ID should be greater than 0, then the diode is what bias? Forward bias.
Sir, unmute.
So if this line is parallel to y-axis, there is no need for you to consider a resistor. But if it has a slope, then there should always be a resistor. Okay. Shall we stop for today? We can have some question answer session. I think you know my phone number. Somebody who, right, my phone number. If you have any doubts, you can even post here.
Hello, sir.
Audible, sir.
Hello, sir.
Yes,
Sir. Hello, sir.
yeah, tell me.
Sir, in page 10F.
Yeah, tell me.
Sir, in page 10F, we can apply that voltage division rule in that circuit.
Page 10.
Yes.
You
Yes,
are
sir.
not
Here,
supposed to apply. The reason is this current is going to split into two currents. Voltage division can be applied only when the same current travels. Same current to 10K, 10K, then you can apply voltage division. Because some amount of current is flowing through 5K also. Then you are not supposed to apply voltage division. Yeah,
sir.
okay. Next.
Hello, sir.
Yes.
Sir, I have doubt in yesterday's problem, sir, that all pass filter ISRO problem.
Ah,
Can we make, can we do by making capacitor as a open circuit?
open circuit. Then there will be some gain, no? That is why it is all pass.
Yes, sir. That's what I'm getting doubt, sir. Then-
Yeah. If you replace a capacitor by short or replace by capacitor by open, your gain will always be 1.
Yes, sir. Yes, sir.
That is why it is all pass. You're right. You can do it. You're right.
Sir, but they have given options all stop filter, no, sir. We
Yeah.
got
See, always remember in an all pass filter, there should be a voltage divider at least which has resistors. One path should be only resistors. That is a indication of all pass. But in all stop filter or band stop filter, you will have capacitors, no? Here one capacitor, there one capacitor.
yes,
But in
sir.
all pass filter, at least there should be one path which has only resistors. So by experience you get, especially all pass filter, you can do by both methods. But band stop filter, in that path you will have one more capacitor that becomes short or open. So you realize that it is frequency selective. But this is
Oh.
not frequency selective. The gain is always 1.
Yes, sir.
Whatever might be the value of that capacitor, gain is 1.
Then if they gave capacitor, then we need to try for,
No,
we need to.
but in that divider, there is only one capacitor here, no? Here there is
For
only
the-
one capacitor in all pass. What I'm trying to say is,
Uh,
there is a divider which has only resistors. So naturally there will be some output, no?
yes, sir. Yes, sir.
That is why.
Sir,
Okay. Yeah.
one more bit, sir. If Rin is infinite,
Ah,
input resistance is infinite. That is why we don't op amp draws no current, right, sir?
in point. Yes, you are right.
Then if it is finite, what happens, sir?
Then we have to calculate. We have to replace op amp by this model and calculate. Let me draw the model. You have to replace op amp by this model. And solve by Kirchhoff's law.
Okay, sir.
This
Then
is
one
Rin,
more.
RID, R0, AVD.
Yes, sir. Yes,
Now
sir.
you apply KVL, you will get it, no?
Sir, one more small doubt, sir. In the statement, we have op amp is a high gain direct coupled differential amplifier, right, sir?
Yeah.
That what is direct coupled, sir? I didn't.
Direct coupled means inside an op amp, we should not use capacitors to couple one stage with the other.
Only resistors.
In olden
should
days,
be-
we used to have capacitive coupling, bypass
Yes, sir.
capacitor, output capacitor, coupling capacitor, all these capacitors we used to use, right, in common emitter, common collector amplifiers in olden days.
Yes, sir.
Now, capacitors cannot be fabricated on an IC. They occupy a lot of space.
Yes, sir. Means,
So
sir,
that is why
resistors
we
should
go
be
for direct coupled on an integrated circuit.
there. Means if capacitors will be there, means only resistors should be there. Inductor
No,
can
if
be.
capacitors are there, suppose the size of an IC is this much. The wafer size is this much. At the tip of a pinhead, suppose on this space, you can make thousands of common emitter amplifiers if they are direct coupled.
Okay.
Thousands, 10,000 common emitters, 10,000 C amplifiers you can make direct coupled. on that much space. But
Yes.
in this big space, one common emitter also you cannot make if it is capacitive coupled.
Okay, sir.
Are you
Okay.
getting?
Yes, sir. Yes, sir. I
Because
got.
capacitors cannot be fabricated on an IC. But in this space you can make. That is why they go for what coupled? Direct coupled.
Yes, sir.
Okay.
Thank you,
Yeah.
sir. Thank you so much, sir.
Okay.
Sir, page number
Page number?
8.
Page number what?
8F.
8. Yeah. This one?
Yeah, I got another answer. Just want to see the question.
Okay, this one you want?
Okay, got it. Okay, sir. So why the diode is logarithmic?
Yeah, see, what do you mean by logarithmic change? Logarithmic change means what is exponential and what is logarithmic? Exponential means expanding of information. Logarithmic means compounding of information. That means a large current you will allow it to flow, but the change in voltage is very, very small, extremely
Right.
small.
Right.
So diode, however the current keeps on changing, the voltage will not change. So it is a switch. Basically, it is a switch. Suppose across the switch, voltage is keeping on changing. You cannot use it as a switch, no?
Right.
Yeah. So diode, however the current keeps on changing, the voltage will not change much. That voltage also, if you neglect, it is a good switch, what I'm saying. But you cannot use it as an amplifier because when you look at the equation, it's misleading, no? ID equal to IS into E power VD by VD. When you see that equation, E power VD by VD, it tells you that if you change VD, there is a large ID that you get, which is not possible because diode does not have
Right.
three terminals. There is no VCC. From where you will get that ID? You cannot get that large ID. There's only one loop in a diode that comes from supply. So VD will change when a current ID flows. So it's something like a resistor here. Resistor is passive, diode is also passive. In resistor, what will happen? You tell me. Some current will flow, resistor will drop.
Right.
How much it will drop? I into R will drop in resistor. Diode, what it will do? Some current will flow, 0.7 drop will be there.
Right.
So diode is a logarithmic device, not an exponential. Are you getting?
Sir, if it is exponential term, why? How did they derive that term? Since it looks
Yeah,
misleading.
if it is an exponential device, then you cannot write VB equal to VT log IC by IS for BJT. The reason is BJT small VB you change from input, you get a large IC from VCC. So that IC, if you allow it to flow through a resistor, you'll get large output. So there, if you connect an output microphone or whatever, small change, hello means hello you will get. In diode, where you will get? In diode, only two terminals are there, no? But here, a change in VB will create a large change in IC. So BJT is an exponential device. Yes, you can define something called transconductance, GM, IC by VB, right? And then you can do amplification. In BJT, yeah, where is this doubts page? Yeah, in BJT, if you bias him in the active region, if you bias him in what region? Active. Here, very cleverly, this 0.7 you have to change. Here, 0.7 only will be there. But if you apply a signal, an audio signal, and you change, you are going to get this big output because BJT is having an extra current VCC. So if he's so sensitive, if you keep changing VB, your IC will dance to the tune of VB, right? It's going to go boom, boom. So he's an exponential. A small change in VB will create a large change in IC. IC equal to IS into E power or A E power VB by VT, you can write. But if you write this equation, people will say, now I'll change, if I change the diode voltage, from where you will get that large current?
Right.
Good.
Okay. Got it, sir. Got it.
Right.
Thank you.
Sir, can we say the
Yes, sir.
transistor is also as a piecewise model?
Who?
Can we draw the transistor into piecewise model?
You want to draw transistor as what?
Piecewise model. Linear
Yes. See, what do you mean by piecewise? The day you may have made an assumption, it is piecewise. The day you say that my BJT is in active region, IC is beta IB. If it fails in active, you will go for saturation. If it fails in saturation, you will go for cutoff. No, the day you are defining three regions, cutoff, active, saturation, it is piecewise linear.
Yeah. Okay. Sir.
Are you getting?
Yes, sir. Yes, sir.
And you have to work at only, please mind you have to work only at one region of the characteristic. Active, 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 active. Fail, go to saturation, saturation, saturation. Fail, come back to cutoff, cutoff, cutoff.
Okay, sir.
Diode, forward bias, forward bias, forward bias, forward bias. Fail, come to reverse bias, reverse bias, reverse bias. Op amp, first linear region. Fail, go to saturation. Fail, come to this region. So that is a beauty here. We are not going to deal with tan hyperbolic, logarithmic, exponential equation. We are saying that we want to convert all these devices with straight line segments. First class, did I tell you? All our devices are lines, that's all. Just
Yes,
with
sir.
lines, we are going to define them. Have you understood?
Yes, sir.
Good.
Okay. Very
Yeah.
basic. Since diode is a current driven, right? It
Yes.
depends on current. So
Yeah.
current is the independent quantity. So
Yes.
and on x-axis we always take the independent quantity. So
What?
on x-axis,
Yeah. See, it is customary that voltage is taken on x-axis and current is taken on y-axis, and we have given the equation. Are you getting?
yes,
But just because voltage is on x, current is on y, it doesn't mean who is dependent on whom. It is just how you wrote the characteristics. We have put a table, VB, VD, ID, VD, ID table they have made. But who knows who is controlling whom, I'm saying.
correct.
Are you getting?
Yes, sir. So in first,
It's just a table. From the table you have drawn X points are there, Y points are there, you have joined the line.
so in first year as well, when we did this experiment in lab,
What?
we actually varied the voltage in first year. When we did it in lab, we actually varied
No,
the
not VB, not VD. You have varied input voltage, no? You have varied input voltage, my dear, not VD. Input voltage you will vary, but you are measuring VD with a voltmeter and ID with a milliammeter. ID you are getting from ammeter, no?
Yes, sir.
VD you will get with voltmeter. These are on readings. From there you have drawn the characteristics.
Okay, sir.
Yeah. You are talking about V in.
Yeah,
Yeah, of course. For getting current, you need some voltage source. That is not. The data is VD and ID. That's all.
Yeah,
Yeah.
the programmable current source actually.
Yeah.
Series with
Yes. Okay. Next.
Hello, good evening, sir.
Good evening.
Yeah, sir, my doubt is like you told that a superposition law can't apply to diodes, right?
Yes. We cannot apply. But if you represent diode as linear, piecewise
Okay.
linear, like how we
Yeah,
are
yeah.
doing.
Okay.
Because see, simple, I'll give you a simple logic. The day examiner says VD 0.7, what do you mean by that? The day examiner says VD is always 0.7. That means X equal constant. What is X equal to constant? X equal to constant. VD is constant. It is a straight line parallel to y-axis, no?
Yeah. Yes.
So the day your examiner says, assume VD 0.7, that means he's already saying that it is linear, no?
Okay.
You see any gate problem, he says VD 0.7. That means he himself is saying that diode is one straight line.
Okay. Yes, sir.
So when diode is a straight line and you will replace diode by 0.7, can't a voltage source of 0.7 allow you to apply superposition? Yes, it will allow you. What is the big deal in that?
Yeah, sir. Yeah. Got it, sir.
Yeah, good.
Thank you so much.
Simple. Please, she has made a very good point here. All of you listen. The day VD equal to 0.7 is not given in exam. The day VD equal to 0.7 is not given in the exam. Then you have to treat diode as what? Non-linear and solve. You have to take ID equal to IS into e power VD by VT.
Yeah.
I will solve such problems also. Okay?
Yeah. Thank you, sir. Got it.
Yeah. Next.
Sir, 32F.
30?
32.
This one?
Yes, sir.
Yeah.
What we call this circuit, like piecewise linear or?
It is, everything is piecewise. Even ideal model is also piecewise linear. Some books say that only this is piecewise linear.
Yes.
It's not like that. Ideal is also linear, piecewise linear. It says that every piece, one piece of the characteristic you have to take, that is piecewise linear. And you have to take only one segment at a time.
1 second.
They say that this one is piecewise linear, and no. Wherever you draw lines, they are all what? Piecewise linear models.
Okay, sir.
Okay.
Hello.
Yeah.
So one more doubt. So if we measure the voltage across diode and measure the current flowing through diode at a given instant of time, so Ohm's law will be valid, right?
No, come again, your voice. If we
measure the voltage across diode at a given instant of time and measure the current with the current ammeter, so across the diode, Ohm's law will be valid, right? V equals to IR.
Yeah, see, always remember one thing. Time is never a factor now. Time has gone. There's no question of time when you apply KVL and KCL. Are you getting?
Yes, sir.
The day you allot a unique value of current, then your entering current through the diode minus leaving current is charge buildup. But this time factor we made 0, then the current entering is current leaving. This is entering current, this is leaving current. That means there is only one current through a diode, ID. The day I write ID, time is gone here. It is, you are allotting a unique value of current. The day you say VD, because in VD, there is no flux linkage, d phi by dt is 0. If you make d phi by dt is 0, you can allot a unique value of voltage. So in my class, there is no charges, there is no place for time, there is no place for flux.
Okay.
If I allot a unique value of voltage, the day I say 0.7, 0.7 morning, 0.7 evening, 0.7 any time, it's not like at a particular time. It's always 0.7, 0.7, 0.7, because time is no longer a factor when you apply KCL. Entering is leaving. Are you getting?
Yes, yes.
Yeah. Don't bring time, charge, and flux linkage. Because if I say d phi by dt is 0, the rate of change of flux in any closed path is 0, then you can allot a unique value of voltage. Zener is going to have a unique value of voltage. We're going to say VZ, that's it. We're going to say diode VD. We're going to say BJT VBE. It's not time, morning VB, afternoon VB, evening VB. You're allotting a unique value of voltage. When you allot a unique value of voltage, there's no flux, there's no time. They're all removed. When you say current, there is no charge, there is no time.
Yes,
so don't talk about depletion inside. Don't talk about rate of change of flux outside. अंदर बात नहीं करना चाहिए, बाहर भी बात नहीं करना चाहिए. Only current, voltage, KVL, KCL. Current, voltage, KVL, KCL. In my class, that's how we may make the subject simple. If you bring so many factors into account, right? Reverse saturation current, time, thermal voltage, this, that, everything, how we can solve problems?
Yes, sir.
Yeah.
Thank you, sir.
Yeah.
Hello, sir.
Yeah.
Sir, I missed some parts. Sir, could you tell what is the difference between directive coupling and that capacitive coupling, sir?
No, direct coupling means directly one stage to the other, we have to connect it with a wire. This is one stage, suppose. Okay. I have another stage. Direct coupling says that you have to give directly like this. If you give directly through a wire, then it is called direct coupling. In capacitive coupling, one stage with the other, you have to isolate with a capacitor like this.
Okay.
Then capacitor. Direct matlab direct de do. Directly you connect. That is called direct coupling.
Then why CE amplifier cannot be fabricated in an IC if it is capacitive coupling, sir?
Because capacitors in the order of microfarad range cannot be because what is microfarad range? You have what is a capacitor? 2 plates separated by dielectric. How much polysilicon you will pour to create 2 capacitors of 1 microfarad on a wafer of this size? Initially, they tried even with planar technology, but they failed. When monolithic technology came, they said that no capacitors, sirf BJT, MOSFET, that's it. Some resistors, okay, even you should maximum avoid. Capacitors, you should be shy of using capacitors. Capacitors cannot be fabricated on an IC. It's very difficult. Old circuits, common emitter, common base, they had capacitors. Now these days you see gate problems, only one MOSFET, one resistor, BJT resistor, like that.
Okay. Got it, sir.
Yeah.
Thank you, sir.
Then, anybody?
Sir, in the second piece of the model at 0.7 volt constant, if we assume that diode has a black box, for a given 0.7 volt, whatever the current we are increasing, the current is continuously increasing, right, sir?
Yes. However, the current increases when you increase the voltage, input voltage, the drop across the diode will not change much.
Can we apply Ohm's law for this in that region?
Can we apply what?
Ohm's law.
Where you want to apply Ohm's law?
In that second part.
That is what I'm saying. You want to apply, you have to already apply 0.7 volts as an assumption.
Okay, sir.
The extra difference will be dropped across the resistor. See here. Suppose I apply 0.7001. I have a resistor and a diode. If I apply 12 volts and then a diode, how we have to solve? First, you should take 0.7. Then leftover 0.00001 will be dropped here. Here you have to take 0.7. Leftover 11.3 will be dropped across. So resistor is not at all demanding anything.
Yes, sir.
Whatever is difference will be dropped. First a diode will take 0.7. So don't think, sir, resistor needs drop. How diode will take point? First he will take diode, but he will not take more. Diode is always on diet. He will give how much you give. He will eat only this much. Difference will be dropped across the resistor to satisfy Kirchhoff's voltage law.
Yes. Fine. Okay, sir.
Okay.
Hello, good evening, sir.
Yes.
Sir, I had a doubt in the gyrator problem. I think it is in 9F.
9F?
Yes, sir. I think.
Yeah.
Just one page before, sir. 8F maybe. Where? Yes, sir. Sir, here I had a doubt where to connect that VT, sir, or V.
Very good. Good doubt you have asked. Now, say for example, I am having a Colpitts oscillator.
Yes.
In a Colpitts oscillator, this is there. Are you getting?
Yes, sir.
Now the inductor is bulky now. It's power thirsty.
Yes.
So you can replace this by a gyrator. That's what I mean.
Yes. No. That. Yes, I could understand that. My doubt was that in that diagram, other diagrams also where we had to calculate Rin, we sometimes we connected it positive terminal. Like in that diagram, if we connect VT at negative terminal, then what will happen, sir? I mean, at inverting terminal. I mean, in the 9F.
Where is it?
8F, I think.
8F. Thank you. This one. Achha,
Yes,
you mean the two terminals where you have to connect?
Yes, sir. Yes, sir.
Very good doubt. Excellent doubt. So what you are trying to say is the gyrator is not like the inductor actually. It is unidirectional there.
Okay.
When it is unidirectional, how is that you have to connect? That is your doubt. Am I right?
Yes, sir.
So
I mean,
that
yes.
how you have to connect, it all depends on the loop gain, in which path you are following the loop. If you see the loop here, the input is this node 1 and the output is node 2. Can you see?
Yes, sir.
So the current flow is always clockwise like this.
Okay. Okay.
So your gyrator input should be at 2 and output, this input, this is the output, so that you get that loop flowing. Are you getting it? The signal will go from 1 to 2 and then it has to go from 2 to 1.
Yes, sir. Back to complete the loop.
Back. So because in oscillator you have to maintain the loop gain equal to 1.
Yes, sir. In oscillator. Okay.
So
sir,
who is deciding? This op amp will decide.
Okay, sir. In that page, if you can go, please. 8F.
8F.
Yes. సార్ ఇందులోని అదే అంటే నాన్ ఇన్వర్టింగ్ టెర్మినల్ కి వీటీ కనెక్ట్ చేసి ఐ ఇన్ చేసాం కదా సార్, అలాగే ఇన్వర్టింగ్ టెర్మినల్ దగ్గర వీటీ కనెక్ట్ చేస్తే ఏమవుతుంది అది అడుగుతున్నాను సార్.
ఇన్వర్టింగ్ టెర్మినల్ దగ్గర వీటీ, ఫర్ ఇన్వర్టింగ్ టెర్మినల్ యు వాంట్ టు కనెక్ట్ వీటీ.
ఎస్ సార్. అప్పుడు అంటే నాన్ ఇన్వర్టింగ్ దగ్గర కూడా వర్చువల్ షార్ట్ వల్ల వీటీ అవుతుంది కదా సార్, కానీ ఐటీ డైరెక్షన్ మాత్రం ఇలా వెళ్తుంది.
నో see here, first of all let me tell you.
Yes sir.
If you want, without a resistor, if you directly connect to inverting, fire will come in op amp. వస్తుంది op amp లో. ఎందుకంటే current limiting resistor, suppose if you directly connect here VT.
Yes sir. Yeah.
This is ground, so this node will be 0. What will be the current I? VT minus 0 by 0. Infinite current will flow.
Okay. Yeah.
మెల్లగా పొగ వస్తుంది.
Yes sir.
Right.
Yes sir. అంటే అందుకే ఇది కరెంట్ టెర్మినల్ అంటారా?
Yes. Now you got it.
Okay. Fine. Thank you very much sir. Thank you very much.
Hello.
Yes.
Sir, yesterday one problem you told me, sir, all pass filter. Sir, that is we got V not by Vn equals 0, no sir?
No, all stop filter.
Yes sir, that is I got doubt, it is all stop or all pass?
All stop, you are right. All stop, not all pass.
When we will get all pass, sir?
The other problem we have done, no, all pass, that feedback capacitor is there, no? You have to replace it with resistor.
Okay.
There is an all stop filter which you are referring to. Am I right? In that, in the feedback resistor capacitor, you remove and connect a resistor, that is all pass. We have done that problem also. All pass filter we have done 1 minus SCR by 1 plus SCR you will get.
Yes sir, I got it.
Yeah. Okay.
Sir, today 2F. 2F sir.
2F. Is this the one?
Sir, here.
Tell me. Yeah, tell me. Your voice is cut. Tell me. Can you see me? Yeah, Venkat, please unmute the student.
Problem English, వాళ్ళ side నుంచి problem.
Hello sir.
అవునా, okay nana. Yeah, tell me.
Sir, any loading effects?
Hello.
Hello sir.
Yes.
Once explain loading effects, sir.
Loading effect means before connecting amplifier, whatever voltage is there, or before connecting load, whatever voltage is there, after connecting load also same voltage should be there. That is loading effect. If I have a voltage with 9K in that problem, if there is some V, same V should be there. After connecting the load, it is become 0.1 V, no? Whenever the voltage decreases, that effect is called loading. By connecting the load, if the voltage decreases, it is called loading effect. That we have reduced by connecting a buffer. Are you getting? What is your doubt? This is the.
Yes, sir, my doubt is loading effect.
Yeah, this is the load. Before connecting the load, I am having suppose 10 volts. After connecting the load, it has fallen down to 1 volt. This is 9K, 1K. This 10 volt fallen down to 1 volt. So this effect is called loading.
Okay.
Now how to remove loading? This 10 volt with 9K, you have to connect it to an amplifier whose input resistance is high and its output resistance is low. Now if you connect 1K here with the gain 1, you are able to get the same 10 volt here. Are you getting?
Okay,
or 10 sin T. Some signal should be there. No?
I see.
So buffer will
sir,
avoid loading effect. Yeah.
Sir, in 29, if you have drawn ideal case, no, sir, ideal diode case, that graph I didn't understood, sir. Please find.
This graph. No, have you understood this graph? X-axis, Y-axis.
Yes, sir. That I understood.
That is the same, no? This one. See, when do you say X is 0? If the line is on Y-axis.
This.
That is this, no?
Sir, I understood.
VD means X-axis. ID means
Sir,
Y-axis.
Sir, how the graph is on negative axis, sir?
How the graph? No, it's not on the negative axis.
I mean,
it is like this, actually. See here. The characteristics, if you see, it is like this, no? The current is 0. So that is why we have put on negative. The current is 0, that's all. For whatever negative voltage that you give, current is always 0. That is a diode equation. Strictly speaking, diode will have an equation like this. See here, diode will have an equation. ID equal to IS into e power VD by VT minus 1. If VD is positive, this value is very large. 1 is neglected. 1 neglected. 1 neglected. So ID is IS into e power VD by VT. This equation we have written. But if VD is negative, if VD is negative, then 1 is large. 1 is large value. This is very small value. Then your ID is minus IS. This is 10 power minus 13 ampere, no? We can make it 0. What is there? Approximately. So the characteristic says that is almost here. There is a small reverse saturation current which flows in negative. That is negative axis. Where is 10 power minus 13? You show me current. I am locating current 0 here. Can you locate where is 10 power minus 13? Is exactly on that line only. Because y-axis, no? Suppose 1 milliamp, 2 milliamp means you can put 10 power minus 13 means it's almost there only. Are you getting? A simple coordinate geometry. Where is current 0 means exactly on x-axis. Voltage 0, y-axis. What is your doubt? Next.
Hello.
Yeah.
Sir, sorry. Before I got disconnected, sir.
Yeah, tell me.
Sir, page number 2F. 2F.
2F. Yeah.
Sir, here if 5K resistor is given to ground, then I2 into 5K equals 0, no, sir?
I2 into 5K is a finite value. Some current is there, no?
Yes, sir, but it is connected to ground, no, sir, actually.
What do you mean by connected to ground?
Sir, here
voltage is 0, no? Current will be there.
Sir, voltage.
Acha, see here, suppose I have 5 volt.
Yes, sir.
This is 1 kilo ohm. And this resistor is ground. Is there not 5 milli flowing?
Yes, sir.
Yes or no?
Yes, sir.
Yeah.
Okay, sir. Thank you.
Anybody else?
Sir,
Yes.
sir, in that same question, after equation 1 and 2, I1 equal to how it?
IY?
From 1 and 2 equation, I1 equal to next step not understand.
Can you tell me the page number?
Same question, sir, 2F.
2F. Okay. Here. Tell me.
From 1 and 2 equation, next step I1 equal to, that is a current division rule, sir.
This one, no, 1 milliampere into 3K by 2K plus 3K.
Yes, sir.
You can apply. I have applied current division because same answer will come. But you can solve the two equations, same answer you are going to get.
Okay, sir. In yesterday class, recognition of filter, low pass, high pass, waveform not understand.
Waveform?
And means omega equal to 0, omega equal to infinity, V out equal to.
What circuit is that?
Low pass filter.
Low pass. Last class, huh?
Yes, sir, last class.
Which one?
Low pass filter.
This one? Oh.
Class
Sir,
starting.
That's from 14th page.
That was in 14th page.
Yes, sir.
16. Yeah, what is your doubt in low pass filter? Tell me.
Omega equal to 0, how V out equal to how V in.
Which sort of low pass filter is that? I will draw. Just tell me What is the number of that filter? I can remember it.
In class starting, third question, sir.
In class starting, third question
Yes, sir.
of that day. Class
Yes, sir.
starting. Third question. Huh?
Yes, sir.
Okay. Yeah, now I got it. Wait. Let me draw it. This is better. Is this the one? Low pass filter. This one?
Yes, sir.
This is the one?
Yes.
Yeah. What is your doubt? Omega 0 or omega infinity?
Both, sir. Omega 0, omega infinity.
Omega 0, capacitors are open, no?
Open, sir.
Some signal will be there, non-zero output.
For same case.
V0 is not equal to 0. But for omega infinity, capacitor is short, no?
Yes, sir.
So this is ground, this is 0. If this is 0, what is this? 0. What is this? 0. What is this? 0. Your output is 0. Low pass only.
When omega equal to 0, capacitor, some current is there.
No, they are open circuits. Directly V in is given here, no? Some output you will get.
In same case, high pass filter, V out equal to 0.
In same case, high pass filter. This is low pass filter which you are asking. Where is high pass? You are asking this only, no? Is there any other doubt you have in another high pass circuit?
In
For
high
low
pass
frequency, you get a non-zero output. For high frequency, capacitor is short. Directly because of virtual ground, you get 0. A non-zero output at low frequency, at high frequency 0 is a low pass filter only.
Okay, sir. Understood.
Yeah.
Hello.
Thanks.
Yeah.
Hello, sir.
Yes.
In today's first and second pages, we have taken that for calculating the V0, we consider plus and minus signs. No, sir.
Plus and minus signs.
We took the loop and we have applied KCL.
Is this a problem you are referring to?
Yes, sir.
Okay.
But we haven't taken the plus and minus terminals for before problems you have explained. So how does
No,
this
where is
problem...
plus and minus? For V0 you are saying?
Yes, sir. We consider.
See,
it
whenever I say
ground.
voltage at any point, it is a voltage at that point with respect to ground.
Okay.
So if I say V0, it is V0 with respect to ground. For this problem also, if I say V0, what do you mean by that? It means that I will take a circuit like this. Whenever I say V0, like this, it means that there is a ground. And if this is plus, see, when I say 2, it means plus 2, no?
Yes,
it is not minus 2. When I say 5, it is plus 5. So whenever I say V0, it is plus. Where is a minus? It is measured with respect to ground node.
So depending upon the problem, we should take these terminals for applying.
No. The reason why I took this terminal is because you want KVL, which deals with voltage, no? Algebraic sum of voltage. So when I say loop, I have to start from ground and I have to come back to the ground. Then only it will cover a loop.
Yes, sir.
Okay. See, I'll give you another example. Suppose there is 3 volt here. In that problem, this is Vn, this is Vp. Are you getting?
Yes, sir.
What is 3? Vn minus Vp, no?
Hmm.
But if this is Vn, the other end is connected to ground. If this is VP, the other end is connected to ground.
Okay.
This is VP, this is VN. Now you apply KVL and see. Whenever I say a voltage, the other end minus is at ground invariably. Minus to plus, minus VN plus 3 plus VP is 0. So your 3 is nothing but VN minus VP. Same thing. Potential difference. Are you getting?
Okay. Yes, sir.
One more example I will give you. One more example is, suppose I say that I am having a VCC supply. A supply of what? Plus 5, VCC. It means that there is plus VCC here, minus is connected to ground.
Okay.
Are you getting?
Yes, sir.
Wherever there are positive voltages, think invariably that the minus terminal is always connected at what node?
Ground.
Ground. Are you getting?
Yes, sir.
Yeah.
Thank you.
Hello.
Yes.
Page number 17.
Page number?
17.
Little louder. 7, huh?
17. 17.
17. Okay, 17. Yeah.
Sir, I missed the part where you were explaining why we are not using the e to the power of t by tau.
See, e power minus t by tau you should apply if you are gut sure that the capacitor is exponentially charging or exponentially discharging. Now, in mathematics course, you have studied that whenever you are doing integration of exponential only is exponential. Yes or no? What is integration of e power x is e power x. That means the current, if it is exponential, then voltage is exponential, agreed. But here what is current? It is constant, I equal to V by R. So when a constant current flows through a capacitor, the capacitor will not be 1 by C integral I dt, it will be I by C of t. So when it is obeying y equal to mx, how you can apply e power x equation? V0, V initial minus V final, e power minus t by tau, you cannot apply. Are you getting? Please apply e power minus t by tau only when the current is exponentially decaying. That will happen in a simple RC network. I will give you a simple example. This example I have already given. Once again, I will tell what is there. The example is, see here, are you listening? Are you listening? Hello? 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 Yeah. Next, anybody else? Hello?
Sir, good evening, sir.
Yeah, good evening.
I just want to know one thing. The concept which we discussed today regarding loading effect, can we relate it to fan in and fan out in digital, sir?
See, fan in is the number of gates which it can drive, no?
I mean,
yes or no? Fan in and fan out, it relates to the number of gates which can it drive. Yes, definitely. There also we have to consider loading. Loading in the sense, there in fan out and fan in, suppose if a BJT is driving,
yes,
suppose it's a TTL logic or BJT is driving, we have to see what sort of beta value that we have to choose so that the transistor will still remain in saturation to drive all those circuits. There also we can consider something like loading. Yes.
Okay, I mean without causing any change in the initial.
Yes, because the transistor parameter should not change, should not come back to active region.
Okay, sir.
Because digital logic means no active, only cutoff and saturation.
Okay, sir. Sir, and another doubt in a sum, there is a op amp with inverting input given, and the feedback path is having a pi sort of resistor network.
Feedback path is having 5 resistive networks.
5 resistors in the sort of pi symbol.
Pi symbol.
Pi symbol.
This we have done in class, no?
Yes, sir. Is there any shortcut to solve this, sir?
No. Extra node will be there. See, the point is,
Yes, sir.
Whenever you have a network like this isolated,
Yes,
it is unlikely. It's difficult because this node, okay, output node,
yeah.
extra an input node is there. You have to apply Kirchhoff's law only. What we can do?
No other shortcut.
Star delta transformation you can do.
Okay,
You have to
that will
convert
be
it.
fine.
This delta pi means delta, no?
Oh, okay.
You can convert it into a star. You can make one single network. But ultimately, again, if you do it, one node extra, same thing will be there.
Okay, sir. But
Okay, if you
even
want
in
to
the-
convert this delta into star, what is that?
Yes, sir. Even in the initial problem, there is a resistor at the output also, sir.
Then it's so here. So it's,
Yes.
you have to apply Kirchhoff's law, no other go.
Oh, okay, sir. Thank you.
The
Sir.
same problem, such problems are given for 10 marks here in IES.
Yes, sir. Yes, sir. So just to know whether is there any shortcut like applying
Shortcut in the sense I actually tried.
Okay.
The delta is becoming star, star is becoming delta, but finally you are not able to combine them. So we are not relieved of the what you call equations. Two equations I am getting somehow.
Yes, sir.
Yeah.
Okay, sir. Thank you, sir.
Okay, good. Still, anybody? Still anybody? Can we wind up? Still anybody else is there? Still anybody else? Or shall we wind up?
Wind up.
Shall we wind up? See, people whom I have not able to answer, for them, I'm again repeatedly telling you, this is my number, you can post your doubts. This is my number, right? Is there anybody else?
Sir, wind up చేసేయండి.
Okay then, we'll wind up for today. Yeah, thank you. Thank you for your patience.
Good night, sir.
Hello, sir.